There's a star out there that shouldn't exist, a star so ancient, so impossibly old, that it seems to mock the very timeline of the cosmos. It's called the Methuselah Star, and its story is one of the greatest mysteries in astronomy. How can a star be older than the universe? That question has haunted scientists since its discovery. It challenges our theories of the Big Bang, the formation of matter, and the very beginning of time. But this is more than just a scientific anomaly. It's a cosmic riddle that reaches into the heart of our understanding of existence. In this video, we dive deep into the mystery of the Methuselah Star, a journey through light, time, and the uncharted edges of the universe, to uncover the truth behind the oldest known star ever found. Let's unravel this cosmic enigma. Let's journey across time and space, from the birth of the universe to the edge of scientific understanding, to uncover the full story behind the Methuselah Star, a story filled with perplexing data, mind-bending implications, and an enduring mystery that still challenges astronomers, cosmologists, and physicists to this day. To begin, we must first step back to the very beginning, or what we think was the beginning. The current scientific consensus holds that the universe began approximately 13.8 billion years ago in an event known as the Big Bang. It was not an explosion in space, but rather an expansion of space itself, an eruption of time, energy, and matter from a single, infinitesimal point. From that moment onward, the universe began to grow, cool, and evolve. Particles formed atoms, atoms formed stars, stars formed galaxies, and within those galaxies, stars lived and died, forging heavier elements in their fiery cores. The early universe was a simple place by today's standards. It was hot, dense, and largely uniform. Hydrogen and helium were the primary building blocks. The very first stars, what we call population 3 stars, formed not long after the Big Bang. These were massive, short-lived giants that burned hot and died young, leaving behind black holes, neutron stars, or dispersing their elements into the interstellar medium. These early stars are theorized but have never been directly observed, because they existed in an era now obscured by time and distance. But then, as the cosmic timeline progressed, the second generation of stars began to form, population 2 stars. These stars had slightly more metal content, meaning they were not purely hydrogen and helium but included traces of heavier elements produced by the deaths of earlier stars. The Methuselah Star is believed to belong to this generation. Its composition and location suggest it is among the very first stars that formed from the primordial chaos following the universe's infancy. Now, what makes Methuselah so unusual is not just its estimated age, but how that age seems to push beyond the boundaries of time itself. HD 140283 is believed to be at least 14.5 billion years old. That's older than the estimated age of the universe by about 700 million years. Let that sink in. If the universe began 13.8 billion years ago, how could a star have formed 14.5 billion years ago? How could anything have existed before existence itself? Of course, the first thing to consider is the margin of error. Scientists know that their age estimates come with uncertainty. The initial calculations for Methuselah's age, based on its luminosity, metallicity, and position on the Hertzsprung-Russell diagram, did include error bars. In fact, they later refined the age downward slightly, to around 13.7 billion years, but even so, it hovers precariously close to, if not beyond, the age of the cosmos. This is not just a minor accounting error. It's a discrepancy that opens the door to fundamental questions about cosmology. To truly appreciate how this age is calculated, we need to understand stellar evolution. Stars follow predictable life cycles based on their mass and composition. By analyzing a star's brightness, temperature, chemical composition, and other properties, scientists can determine where it falls in that life cycle, and from there, estimate how long it has existed. Methuselah is a subgiant, meaning it has already passed the hydrogen-burning main sequence stage, and is now fusing helium and other heavier elements in its core. That means it has already lived through billions of years of relatively stable stellar life. Its low metallicity, meaning it contains very few elements heavier than helium, confirms its primordial origin. In astronomy, metallicity is not about iron and steel but about all elements heavier than helium. Since heavier elements are forged in stars and supernovae, a low-metal star must have formed before many stars had died to seed the universe with metals. Methuselah is so metal-poor that it likely formed just after the first generation of stars went supernova, enriching the surrounding gas just enough for Methuselah to coalesce. That gives us a relative timestamp, very early in the universe's timeline. But how did we even find this star, and how do we know it's not just a mistake or a miscalculation? Methuselah has been known to astronomers for over a century, but it wasn't until recent decades, with advanced parallax measurements from satellites like Hipparcos and Gaia, that we could determine its distance, motion, and intrinsic brightness with great precision. And with better distance data comes better age estimates. By using stellar evolution models and cross-referencing chemical abundances, researchers like Howard Bond and his team at Pennsylvania State University were able to publish refined age estimates that still flirt with the impossible. Even with corrections for updated cosmological parameters, Methuselah remains one of, if not the oldest known stars ever observed. So what does it all mean? One possibility is that our models of stellar evolution are incomplete. Maybe stars can live longer than we think, or perhaps we are underestimating the time required for stars to evolve based on metallicity and other factors. Another possibility is that our estimate for the age of the universe needs adjustment. Could the universe be older than 13.8 billion years? Mainstream science would say no. The 13.8 billion year figure is based on detailed measurements of the cosmic microwave background radiation, particularly those from the Planck satellite. This radiation is the afterglow of the Big Bang and offers a snapshot of the universe just 380,000 years after its birth. By measuring tiny fluctuations in temperature and density across the sky, scientists can model the universe's age with remarkable accuracy. The idea that the universe is younger than some of its stars isn't just counterintuitive, it threatens the entire framework of modern cosmology. And yet, Methuselah persists. It sits in our galaxy's halo, orbiting through the Milky Way at high speed, a relic from the dawn of time. It bears witness to a universe that has changed, expanded, cooled, and evolved around it. Like a cosmic archaeologist, it holds secrets of an age long gone, perhaps pointing us toward physics not yet understood, or epochs not yet imagined. In the coming segments of this video, we will dive deeper, far deeper, into every aspect of this paradox. We will examine the precise data used to estimate Methuselah's age. We will dissect the structure and chemical makeup of the star. We will explore the implications for cosmology, including alternative theories of the universe's origin, evolution, and fate. We'll talk about quantum fluctuations, time loops, multiverse theories, the reliability of radiometric dating on a galactic scale, and the philosophical implications of an object that seemingly exists before time. We will consider whether Methuselah is truly unique, or whether there may be others like it, hiding in the shadows of the galaxy, waiting to tell their ancient stories. And most intriguingly, we will speculate on what it might mean if Methuselah really is older than the universe, or if it hints at something even more radical, a pre-Big Bang reality, a cyclic cosmos, or evidence of cosmic inflation models that stretch our minds to the limits. As we continue this journey, one thing will become clear: the Methuselah Star isn't just a puzzle. It's a mirror. A mirror that reflects the boundaries of our knowledge, the gaps in our understanding, and the awe that comes from staring into the cosmic unknown. Methuselah, as we continue to observe it, remains an object of extreme curiosity not just because of its age, but because of what it represents, a living contradiction to our understanding of time and origin. Its trajectory across the sky isn't merely random. This star, with its high velocity and peculiar orbit, cuts through the plane of the Milky Way, indicating that it didn't form in our galaxy. It likely originated from a dwarf galaxy that was absorbed by the Milky Way in its early history. That would place Methuselah not only among the oldest stars, but among the oldest intergalactic immigrants, carrying with it the story of a time before the Milky Way as we know it even existed. The notion that Methuselah came from a different galaxy entirely adds yet another layer to the mystery. Galaxies have been colliding and merging since the earliest epochs. These ancient mergers are largely lost to time, their remnants scattered as stellar streams and halo populations. Methuselah is one such fossil, a relic from a vanished past, traveling on an elliptical orbit that takes it high above and below the galactic plane, unlike most stars in the disk which orbit relatively neatly. This halo orbit is key, because it isolates Methuselah from the later generations of star formation, preserving its pristine chemical fingerprint. Now let's talk about that chemical fingerprint. When scientists look at Methuselah through high-resolution spectrographs, what they find is fascinating. The star contains incredibly low amounts of iron and other metals, about 1/250th the amount found in our Sun. That places it in the extremely metal-poor category, suggesting it formed very early, just after the universe began to form its first complex elements. Elements heavier than hydrogen and helium were not created in the Big Bang. They had to be forged in stars and supernovae. Therefore, stars with low metallicity must have formed before many supernovae had polluted the interstellar medium with those elements. In that sense, Methuselah is like a message from the universe's earliest epochs, sealed in a bottle and sent across cosmic time. This composition does more than tell us about age. It also tells us about the processes that occurred in the universe's infancy. For example, the presence or absence of specific elements like lithium, oxygen, and carbon gives us insights into the nucleosynthesis pathways that were active at the time. Interestingly, Methuselah shows an anomalously low lithium abundance. According to the Big Bang nucleosynthesis model, lithium should be present in predictable amounts. But the so-called cosmological lithium problem persists. Many ancient stars have less lithium than expected. Methuselah is no exception. This suggests that either our understanding of how lithium behaves in stellar interiors is incomplete, or that some other process, possibly exotic physics, or even dark matter interactions, may have played a role in depleting lithium from these early stars. Speaking of dark matter, this brings us to another profound aspect of Methuselah's story, its implications for the large-scale structure of the universe. The existence of stars like Methuselah supports the hierarchical model of galaxy formation, where small structures formed first, and then merged to create larger galaxies. It implies that even in the earliest stages of the cosmos, clumps of gas were collapsing under gravity, forming stars and proto-galaxies in regions seeded by dark matter. These dark matter halos acted as scaffolding for baryonic matter to gather and begin the process of stellar evolution. Methuselah is likely a child of one of these first structures, a luminous artifact of those first clumps in the dark matter web. Now consider this: the universe began not in a moment of light, but in darkness. The first 400,000 years after the Big Bang were opaque, filled with a hot, dense plasma of photons, electrons, and protons. Light couldn't travel freely. It wasn't until recombination, when electrons and protons combined to form neutral hydrogen, that the universe became transparent. The light from that moment, the cosmic microwave background, is our oldest view of the universe. But stars like Methuselah formed long after that light had decoupled. They're not just ancient. They are witnesses to the very beginning of structure itself. And yet, even with all of our tools, our satellites, our simulations, we are left with this stubborn paradox: the star seems older than the universe. To understand this conundrum, we need to dive deeper into how age is estimated, both for stars and for the universe. Stellar ages are calculated using models of stellar evolution. These models simulate how stars of different masses and compositions evolve over time. For a given mass and metallicity, a star's temperature and luminosity tell us how long it's been burning fuel. Methuselah's position on the Hertzsprung-Russell diagram, the graphical representation of stellar temperature versus luminosity, places it on the subgiant branch. This phase occurs just after a star exhausts hydrogen in its core and begins to burn hydrogen in a shell around a helium core. It's a relatively short phase in the stellar life cycle, and its characteristics are well understood. Thus, Methuselah's age estimate is relatively robust. But it still comes with uncertainties. The age estimate of 14.46 plus or minus 0.8 billion years means that the lower bound of the age could be around 13.66 billion years, just barely under the universe's age. Yet even that lower bound is troubling. It means Methuselah could have formed within 100 million years of the Big Bang. That would be incredibly early, considering that the first stars are thought to have formed around 150 to 200 million years post-Big Bang. Could it be that the timeline of star formation needs revision? Or perhaps, our model of the Big Bang itself? Let's now turn our gaze to the other side of the equation, the age of the universe. This figure, 13.8 billion years, comes primarily from measurements of the cosmic microwave background and the expansion rate of the universe, the Hubble constant. But even here, there is debate. Different methods of measuring the Hubble constant yield different results. The Planck satellite, observing the early universe, gives a value of about 67 km per second per MPC, leading to an age of 13.8 billion years. But measurements based on the local universe, using Cepheid variables and type I supernovae, suggest a higher Hubble constant, around 73 km per second per MPC, which implies a younger universe, closer to 12.8 billion years. This discrepancy, known as the Hubble tension, is one of the most active areas of research in cosmology today. Some scientists believe it points to new physics beyond the standard model. Perhaps dark energy evolves over time. Perhaps gravity behaves differently at cosmic scales. Or perhaps there was a period of early dark energy that briefly accelerated expansion, changing the calibration of our age measurements. Now imagine the implications. If the true age of the universe is actually closer to 12.8 billion years, and Methuselah is older than 13 billion years, then the paradox deepens. Instead of reconciling the numbers, we're pulling them further apart. It's like finding an ancient fossil embedded in rock supposedly laid down after the creature died. It calls into question the reliability of our tools, our assumptions, or even our entire model of cosmic history. Could Methuselah, then, be a clue to something far more profound? Some fringe theories have suggested radical ideas. One possibility is that the universe underwent a phase before the Big Bang, a kind of cosmic gestation. In some versions of string theory and quantum gravity, the Big Bang is not the beginning but a bounce from a previous contraction. This cyclic model of the universe allows for the possibility that stars, or at least matter, existed before the Big Bang. While these theories are highly speculative, they illustrate just how disruptive an object like Methuselah can be. It forces us to re-examine foundational concepts and entertain ideas that were once relegated to the realm of science fiction. Another radical idea is the possibility of variable fundamental constants. If the speed of light, the gravitational constant, or other fundamental values were slightly different in the early universe, it could affect everything from nucleosynthesis to stellar evolution. Even tiny variations could alter age estimates. It's a mind-bending concept that the laws of physics may not be constant across time and space, but it's not ruled out by any current observations. In fact, some distant quasars have shown possible signs of varying constants, though the evidence is far from conclusive. Methuselah, then, becomes a kind of Rosetta Stone, not for deciphering ancient languages, but for deciphering the hidden grammar of the cosmos. It speaks to us not in syllables but in spectra, not in syntax but in stellar evolution. It beckons us to look deeper, to question more bravely, to expand our minds beyond what is convenient or conventional. Let's pause to reflect on the irony here. We often think of stars as symbols of permanence and predictability. They twinkle overhead, fixed in their constellations, faithful guides to travelers and dreamers alike. Yet here is a star that does the opposite. It destabilizes our confidence. It shows that even the heavens can lie, or at least confuse. And in doing so, it elevates our understanding. For the universe, after all, is not obligated to make sense to us. It is under no obligation to conform to our models or our mathematics. Our theories are approximations, shadows on the cave wall, and sometimes, it takes a single anomaly, a single ancient, metal-poor subgiant, to remind us of just how much we still do not know. And so we look again at the Methuselah Star, not just with instruments and algorithms, but with philosophical awe. The sheer existence of such a star makes us confront an uncomfortable truth, that we might still be at the dawn of understanding our universe. The contradiction between Methuselah's estimated age and the age of the universe isn't simply a technical discrepancy. It might be a symptom of a deeper, hidden truth waiting to be uncovered. One might imagine that, over time, the data would resolve this tension. Perhaps a revised parallax measurement from Gaia, or more refined stellar models, would gently shift the age downward. But that hasn't happened, at least not decisively. Instead, the Methuselah Star stubbornly clings to its reputation as the most enigmatic beacon in our cosmic neighborhood. It's a witness to an epoch we can barely imagine. And it's telling us that the early universe might have been more efficient, more active, or even more chaotic than we've allowed ourselves to believe. Let us now look more closely at the observational journey that brought us to this star. HD 140283 was first catalogued long ago, but it wasn't until modern high-resolution spectroscopy and space-based parallax measurements that its true significance became apparent. It lies just 190 light-years away, practically in our cosmic backyard. And yet, this nearby, unassuming subgiant turned out to be one of the oldest entities we've ever observed. The precision of measurements matters immensely here. When the Hubble Space Telescope trained its instruments on HD 140283, the goal was not just to observe it, but to determine its distance with unprecedented accuracy. This parallax-based distance allowed astronomers to better constrain the star's intrinsic brightness, which in turn informed stellar evolution models. With improved input parameters like temperature, metallicity, and luminosity, researchers were able to derive a more accurate age. It's important to note the challenge of these stellar models. Estimating a star's age isn't like counting rings in a tree. Stars don't have clocks inside them ticking off eons. Instead, their observable properties, like their brightness and color, must be compared against theoretical models. And these models are sensitive to a host of factors: opacities, mixing lengths, nuclear reaction rates, elemental abundances, and even the treatment of convection and diffusion. Even small adjustments in these assumptions can shift a star's estimated age by hundreds of millions of years. That's why the plus or minus 800 million year uncertainty in Methuselah's age is so crucial. It's not just statistical noise, it represents the frontier of our astrophysical knowledge. What's more, the fact that this uncertainty still places the star perilously close to or beyond the universe's age shows just how finely balanced our cosmic chronometers truly are. Now imagine the timeline in your mind. The Big Bang occurs. The universe cools. First, there's darkness, just hydrogen, helium, and a few trace elements floating in an expanding void. Then, gravity begins its eternal work, pulling matter into clumps. Eventually, pressure and temperature rise. Nuclear fusion ignites. Light returns. The first stars, population 3 stars, are born. They live fast, die violently, and seed the cosmos with heavier elements. Methuselah was not one of those first stars, but it may have been born in their immediate aftermath. It belongs to population 2, ancient, metal-poor stars that formed after the earliest explosions enriched the primordial gas clouds. These population 2 stars, including Methuselah, are rare and precious to astronomers. They contain the elemental fingerprints of the earliest nucleosynthesis events in the universe's history. There's something poetically fitting about the name Methuselah. In the Bible, Methuselah is the longest-lived human, said to have lived 969 years. He represents endurance, legacy, and a life that spans beyond comprehension. The star Methuselah does the same on a cosmic scale. It is a relic that has outlived entire galaxies. It has seen the rise and fall of stars, clusters, and perhaps even civilizations. Its atoms have endured through every cosmic epoch, untouched and unchanged. Now consider the broader implications. If Methuselah is not unique, if there are other stars like it hiding in the galactic halo or in distant globular clusters, then what does that say about our cosmic history? Could it be that the universe's first stars formed even earlier than we thought? Or that our models of structure formation need revision? Perhaps it's time we reconsider the speed at which galaxies assembled. Traditional models suggest a gradual buildup of galaxies over billions of years. But what if the first proto-galaxies formed rapidly, birthing long-lived stars like Methuselah in the blink of a cosmic eye? That would suggest a universe that got off to a much faster start than we've allowed for in our simulations. Alternatively, we might consider more exotic ideas. What if some of our constants are not truly constant? If the gravitational constant or the fine structure constant were slightly different in the early universe, it could impact the rate at which stars form and evolve. These variations would ripple through the cosmic timeline, affecting everything from the formation of atoms to the brightness of supernovae. It's a radical idea, but one not without precedent. Some cosmologists have proposed that constants like the speed of light or the strength of gravity might be dynamic quantities, changing subtly across time or space. If so, then the models we use to estimate the universe's age might need to be recalibrated. Methuselah could then fall neatly into place within a revised framework, no longer an anomaly, but a clue that helped unlock a new paradigm. And there's another fascinating question. Could Methuselah have formed from the debris of a population 3 star? That is, could its low metallicity reflect the fact that it formed in a region touched only lightly by the first supernovae? If so, then it carries within it the ashes of the first stars, the fingerprints of events that no longer leave light behind. This makes Methuselah not just a relic, but a bridge, a living link to the very first moments of cosmic alchemy. Let us not forget that the tools we use to study these stars, telescopes, spectrometers, satellites, are only as good as the models and minds behind them. And as our technology improves, so too will our ability to refine these measurements. The James Webb Space Telescope, for example, is already peering into the distant universe, capturing light from the first galaxies. With such data, we might begin to place Methuselah in a richer context, comparing it not just to models, but to actual stars observed from the dawn of time. But perhaps the most astonishing thought is this: Methuselah is still burning. Despite its age, it continues to shine, steadily, quietly, resolutely. It has outlived billions of stars. It has watched countless suns rise and fall. And it will likely outlive many more. It may even survive long enough to watch the Milky Way collide with the Andromeda Galaxy in a few billion years, drifting silently through the chaos, untouched and unbothered. Methuselah is a cosmic lighthouse, casting light not just across space, but across understanding. It tells us that the universe is more ancient, more complex, and more wondrous than we ever imagined. It reminds us that even our most cherished models must yield to evidence. And it invites us, compels us, to keep looking deeper. Because in the vast silence of space, one star's whisper can change everything. Its whisper, soft yet profound, carries with it the untold stories of a universe still in its infancy. Methuselah Star, in its unassuming glow, stands as a silent sentinel of time, watching, glowing, enduring. But what secrets has it kept hidden in the depths of its hydrogen and helium core? What truths does it embody simply by existing longer than it should, longer than cosmic logic would allow? To understand this paradox more deeply, one must take a journey through the science of stellar aging. Stars like Methuselah are not born with a clock attached, nor do they age in predictable, linear ways. Their lifespan is dictated by their mass, their chemical composition, and their internal processes, all of which must be reverse-engineered from surface observations. Methuselah, with its low metallicity and distinct spectral fingerprint, indicates a composition that lacks many of the heavier elements formed in later generations of stars. This makes it not just ancient but chemically primitive, a true stellar fossil. Such low metallicity stars are called population 2 stars, but among these, Methuselah is a standout due to how close it is to what scientists term zero metallicity. Stars with zero metallicity, known as population 3 stars, are purely theoretical. None have ever been directly observed. They were thought to exist only in the first few 100 million years after the Big Bang, born from the untouched hydrogen and helium created during primordial nucleosynthesis. While Methuselah is not quite one of these, it's as close as we've come in the observable universe. Now consider the implications of its chemical fingerprint. Methuselah contains slightly more heavy elements than a pure population 3 star would, suggesting it formed shortly after the first stars exploded as supernovae. These supernovae spewed the first heavy elements, carbon, oxygen, iron, into the interstellar medium. When Methuselah coalesced from these remnants, it retained only trace amounts of these elements, giving it the unique signature we observe today. Thus, Methuselah is not just old, It is a direct descendant of the universe's first epoch of stellar death and rebirth. This paints a more vibrant picture of the early cosmos, one where explosions were common, space was opaque with dust and gas, and the first ingredients of planets, people, and galaxies were only beginning to brew. If Methuselah formed during that time, it may have existed when galaxies were still chaotic clouds of gas, colliding and merging rapidly, unshaped by the orderly structures we see today. And yet, it has survived. Most stars of such ancient lineage reside in dense environments where gravitational interactions could disrupt or even destroy them. Methuselah, on the other hand, lives in relative isolation in the Milky Way's halo, a region of ancient stars and globular clusters. Its orbit is highly elliptical, carrying it high above and below the galactic plane. This strange orbit, too, tells a story. Perhaps Methuselah was once part of a smaller satellite galaxy that was absorbed by the Milky Way, its stellar core remaining intact while its surroundings were ripped apart. This possibility opens the door to even more exotic scenarios. What if Methuselah didn't form within the Milky Way at all? What if it was born in a dwarf galaxy or a globular cluster that no longer exists, torn to shreds by tidal forces over billions of years? This would make it not just ancient, but a refugee from a forgotten galactic civilization, an orphaned sun adrift in a foreign sky. Its survival, then, would be not only a matter of stellar endurance but of galactic archaeology. And yet, for all its mystery, Methuselah has given us answers too. Its age has allowed astronomers to place firm lower bounds on the age of the universe. If the star is about 14.5 billion years old, then the universe must be at least that old, or something in our assumptions must be corrected. This is where cosmology meets stellar astrophysics in a delicate dance. Estimates of the universe's age rely on our interpretation of the cosmic microwave background, the large-scale structure of galaxies, and the Hubble constant. But each of these is laced with uncertainty, especially the latter. The Hubble constant, the rate at which the universe is expanding, has become a point of fierce debate. Different methods of measurement yield different values. Observations of nearby supernovae suggest one number. Measurements of the early universe through the Planck satellite suggest another. This discrepancy, known as the Hubble tension, remains one of the most pressing mysteries in modern cosmology. And Methuselah quietly exacerbates this tension. Its existence lends weight to the idea that our estimates of cosmic age may be off, perhaps due to misunderstandings about the early universe's behavior, or due to new physics we have yet to uncover. Could there be an unknown energy component that altered the universe's expansion rate? Could dark energy have behaved differently in the past? Could there be more fundamental flaws in our cosmological model? To resolve these questions, we must turn to the synthesis of disciplines: cosmology, nuclear physics, stellar evolution, galactic archaeology, and quantum theory. Methuselah is not just a star to astronomers. It's a point of convergence for every major theory in physics. Its anomalous age acts like a pressure point, exposing the stress fractures in our understanding. It forces physicists to scrutinize assumptions about dark matter, dark energy, inflation, and even quantum gravity. Some theorists have even proposed that Methuselah might point toward a cyclic, or bouncing universe model, one in which the Big Bang was not the beginning, but merely the latest episode in an eternal cycle. In such models, a prior universe could have collapsed, or crunched, into a singularity and then exploded outward again in a new Big Bang. In this framework, Methuselah might have formed from the material remnants of a previous universe, a notion almost mythic in scope, and yet increasingly entertained in theoretical physics circles. While these ideas remain speculative, they demonstrate the extraordinary role Methuselah plays in modern scientific thought. Like a pebble in a pond, its existence creates ripples that spread through every corner of our cosmological framework. And all of this, every equation, every hypothesis, stems from a single, unremarkable point of light in the sky, barely visible without a telescope. It's a humbling thought that one star, a mere speck in the cosmos, could destabilize the most elegant theories humanity has ever constructed. It speaks to the power of observation, the importance of anomaly, and the necessity of humility in science. For every rule we think we've written into the cosmos, There is always an exception waiting to be discovered, a quiet star at the edge of what we think we know. The journey of understanding Methuselah is also a testament to collaboration. From Hubble to Gaia, from ground-based telescopes to theoretical laboratories, hundreds of scientists have contributed to peeling back its layers. Each observation adds resolution to the picture. Each calculation chisels away the uncertainty. Yet the full truth still eludes us. Like an ancient monolith, Methuselah offers glimpses into the past but guards its ultimate secret with silence. Even the name Methuselah, given by humans, steeped in mythology, adds a poetic weight. It invites us to think in mythic terms, to see the universe not only as a machine of physics but as a canvas of meaning. In the face of such age, we are all young. All civilizations, all planets, even all galaxies are children compared to this single sun. And that changes how we see ourselves. Methuselah is more than just a star. It's a mirror held up to the universe, and to us. It shows us what it means to persist. What it means to endure the tempests of cosmic time. What it means to quietly witness the birth, transformation, and possible end of all things. And as we continue to decode its message, we may find that the answers we seek about the universe are not somewhere out there, but hidden in the light of a single star. And so the story deepens, spiraling into yet more questions that stretch the fabric of human understanding. Methuselah Star stands not just as a scientific puzzle, but as a symbol of everything we have yet to learn about the cosmos. If a single star can challenge the age of the universe, what else might the heavens be hiding in plain sight? To explore this further, we must dive into the tools, techniques, and theories that scientists have developed to try and make sense of Methuselah's paradoxical existence. Chief among them is stellar modeling, a complex method of simulating a star's life cycle using equations of nuclear physics, thermodynamics, and hydrodynamics. These simulations consider everything from the fusion reactions occurring at the core to the opacity of outer layers, to the diffusion of elements over time. But even with the most advanced models available, Methuselah does not easily conform. The key inputs for modeling a star's age include its mass, luminosity, radius, temperature, and metallicity. Of these, metallicity plays a central role, as it directly affects the star's rate of fuel consumption. Metal-poor stars like Methuselah burn their hydrogen slowly and steadily, allowing them to live far longer than metal-rich stars like our Sun. This slow-burning nature is what gives Methuselah its incredible lifespan. Yet the models that account for this extended life still fall short of explaining how a star could be older than the universe itself. One explanation might lie in the assumptions we make about the input data. Perhaps the star's distance from Earth was miscalculated, or maybe its luminosity was underestimated, leading to skewed results. But modern telescopes, especially the Gaia Observatory, have significantly reduced these uncertainties. Gaia's astrometric data has pinpointed the star's location, motion, and distance with unprecedented accuracy. These measurements confirm Methuselah's high velocity and elliptical orbit through the galactic halo, characteristics consistent with an ancient star born in the earliest epochs of the Milky Way or even earlier. That elliptical orbit is no coincidence. Stars in the galactic halo often have orbits that are highly eccentric, suggesting a violent past. Methuselah's orbit carries it tens of thousands of light-years above and below the Milky Way's disk, into the sparsely populated outskirts of our galaxy. This motion implies that it did not originate in the same calm, rotating disk where our Sun was born. Instead, it may have come from a dwarf galaxy that merged with the Milky Way in its chaotic youth. That merger could have hurled Methuselah into its current trajectory, preserving it as a relic of a lost world. And that lost world, if it existed, was not like the Milky Way we know today. In the early universe, galaxies were smaller, irregular, and prone to frequent collisions. They were bursting with newborn stars and flooded with ionizing radiation. In such a turbulent environment, the very survival of a fragile, ancient star seems unlikely. Yet Methuselah endured. Perhaps it formed in a pocket of relative calm, or perhaps it was born massive enough to escape the gravitational chaos around it. Whatever the case, its survival makes it not only rare but uniquely valuable. That value is not just academic. Understanding Methuselah could provide critical clues for the study of exoplanets, galactic formation, dark matter, and the early universe. For example, if Methuselah formed shortly after the first generation of stars exploded, then it may have formed in a metal-poor environment just enriched enough to allow rocky planets to condense. This opens the question, could it have once hosted planets? Could those planets have persisted across billions of years, harboring life in complete secrecy? It's a tantalizing but deeply speculative thought, yet it illustrates the potential depth of what Methuselah represents. Even more profound is Methuselah's influence on cosmological models. The current age of the universe, approximately 13.8 billion years, is based on the lambda-cold dark matter lambda CDM model, a framework that explains the expansion of the universe, the role of dark energy, and the structure of the cosmic microwave background. But Methuselah challenges this model at its very core. If its age estimate of 14.5 billion years holds, then either our understanding of the star is flawed, or the entire cosmological framework needs revision. This has led some scientists to explore alternative theories. One suggestion is that the cosmological constant, lambda, is not actually constant, but evolves over time. Another is that dark energy may interact with dark matter in unknown ways that alter the rate of cosmic expansion. These ideas remain at the fringe, but Methuselah adds weight to the urgency of exploring them. More radical still are the implications for time itself. Some physicists have proposed that time may not be a fixed, linear dimension, but an emergent property of quantum processes. If time is more fluid than we understand, then measuring the age of anything becomes a far more complex task. Methuselah might not be older than the universe in any absolute sense, but rather, our perception of age might be incomplete or relative, dependent on the frame of reference in which it's measured. This plunges us into the domain of theoretical physics, where string theory, loop quantum gravity, and even multiverse concepts begin to appear. Could Methuselah be evidence that we live in a universe that emerged from a previous one, or that it has interacted with a parallel dimension? Could the star be a holdover from a quantum fluctuation that predates the Big Bang? These questions are fantastical, but they highlight just how disruptive Methuselah's existence truly is. It tears at the very seams of what we think we know. And while theoretical debates rage on, Methuselah continues to shine with quiet indifference. Every night, it traverses the sky, radiating photons that began their journey centuries ago. Observing it is like peering through a window not just into deep space, but into deep time. Every measurement we take brings us closer to decoding its ancient song, even as that song continues to defy our understanding. Methuselah also invites reflection on our place in the cosmos. Compared to its age, the entirety of human civilization is but a blink. Every empire, every discovery, every war, and every work of art has occurred during the briefest flicker of this star's life. It reminds us that the universe is vast not only in space, but in time. We are temporary guests in a realm of near-eternal endurance. And yet, despite our brevity, we have discovered Methuselah. We have puzzled over it, argued about it, and built machines to study it. That alone is a kind of triumph. It speaks to the power of human curiosity, our refusal to accept the universe at face value. In the light of Methuselah, we see not only the past, but the future of science, a future built on the shoulders of mysteries like this one. We return now to the deeper layers of the Methuselah Star's paradox, probing not only its age but what its very presence tells us about the structure and evolution of matter in the cosmos. As we observe this ancient body suspended in space, burning quietly for over 14 billion years, or so we estimate, it becomes necessary to re-examine how we define and measure stellar time itself. Methuselah, or HD 140283, is classified as a subgiant star. This means it has passed the main sequence stage of stellar evolution, during which it steadily burned hydrogen in its core. Now, with its hydrogen nearly exhausted, the star is shifting toward helium fusion. In this subgiant phase, its outer layers have expanded and cooled slightly, yet it has not yet reached the dramatic instability of a red giant. This is a relatively brief stage in a star's life, but it offers a treasure trove of diagnostic features that astronomers can use to estimate age. Stellar ages are notoriously difficult to determine with precision. While we can measure properties like temperature and composition directly through spectroscopy, age must be inferred indirectly through models of stellar evolution. These models rely on our understanding of nuclear physics, the behavior of plasma, and thermodynamic principles under conditions vastly different from those we can replicate on Earth. A small error in one input, such as metallicity, which affects a star's opacity and energy transport, can yield significant discrepancies in the resulting age. Methuselah's extreme metal-poor nature is a primary clue to its antiquity. In astrophysics, metals refer to all elements heavier than helium, including carbon, oxygen, and iron. The earliest stars in the universe, known as population 3 stars, contained almost no metals at all. These first-generation stars forged heavier elements in their cores and seeded them into the universe through supernovae. Subsequent generations, known as population 2 and population 1 stars, formed from clouds enriched by this stellar debris. Methuselah is classified as a population 2 star, meaning it formed after the first stars, but still very early in cosmic history. Its metallicity is less than 1/250th that of our Sun. This supports the theory that Methuselah formed shortly after the first supernovae began to enrich the interstellar medium, making it one of the earliest stars that could support long-term hydrogen burning. But even within population 2 stars, Methuselah is exceptional. Its low metal content combined with its mass and luminosity places it in a very narrow window of stellar evolution models that indicate an age older than 14 billion years. That estimate initially seemed to defy the entire framework of cosmology, because the universe itself, based on measurements of the cosmic microwave background and expansion rate, is only 13.8 billion years old. This leads us to consider how we estimate the age of the universe. The current best estimate comes from observations of the cosmic microwave background (CMB) radiation, particularly data from the Planck satellite. This radiation is the afterglow of the Big Bang, and by measuring its fluctuations, scientists can calculate parameters like the Hubble constant, which tells us how fast the universe is expanding. When combined with general relativity and the lambda-CDM model, this expansion rate yields an age of roughly 13.8 billion years. But that number assumes certain constants remain, constant. The Hubble constant, for instance, has been a source of intense debate in recent years. Measurements based on CMB data, the early universe, differ from those based on supernovae and Cepheid variables, the local universe. This discrepancy, known as the Hubble tension, suggests that we may not fully understand the physics governing cosmic expansion. If the true value of the Hubble constant is different from what we assume, then the estimated age of the universe could shift. Some cosmologists argue that if the Hubble constant is slightly lower than previously thought, the universe could be older, perhaps by several 100 million years. That adjustment might be enough to accommodate Methuselah's estimated age. Others propose more exotic solutions, perhaps dark energy changes over time, or there is a previously undetected particle influencing the evolution of the early universe. Yet even as cosmologists revise their models, astronomers working on Methuselah's age have refined their measurements, too. Over the years, as better data became available from instruments like Hubble and Gaia, new calculations revised Methuselah's age downward, from an original estimate of 16 billion years to a more conservative 14.27 plus or minus 0.38 billion years. This updated range just barely intersects with the age of the universe, suggesting the paradox may not be a contradiction after all, but instead a remarkable convergence that challenges our margins of error. However, this slight overlap doesn't make the Methuselah Star any less extraordinary. If anything, it confirms just how finely tuned our understanding of stellar and cosmic evolution must be. This star's age is not just an isolated data point, it is a stringent test of everything we claim to know about how stars form, evolve, and die. Methuselah's motion also reinforces its status as an ancient cosmic traveler. Its proper motion through the sky is among the highest for any known star, indicating that it's relatively close to us, only about 190 light-years away. Its high speed and elongated orbit through the galactic halo suggest it does not belong to the main population of stars in the Milky Way's disk. Instead, Methuselah likely originated in a primordial dwarf galaxy that was later assimilated into our own. This possibility is supported by recent studies of galactic archaeology, a field that reconstructs the history of the Milky Way by studying its oldest stars. Researchers have found that many halo stars with low metallicities and high velocities are remnants of ancient galactic mergers. If Methuselah is one such remnant, then it is not only a time capsule of early star formation, but also a fossil of a vanished galaxy, a witness to the chaotic birth of the Milky Way. This line of inquiry leads us to the broader topic of stellar fossils, stars that carry the chemical fingerprints of the early universe. By studying the ratios of elements like iron, magnesium, carbon, and lithium in these stars, scientists can reconstruct the timeline of nucleosynthesis across cosmic epochs. Methuselah's composition, in particular, offers vital clues. It contains slight traces of elements heavier than helium, indicating it was born after the first supernovae, but before heavier enrichment events became common. Intriguingly, Methuselah contains a small but measurable amount of lithium, a fragile element that is thought to have formed in the first minutes after the Big Bang. The amount of lithium in the universe has long been a puzzle, because Big Bang nucleosynthesis models predict more lithium than we observe. Methuselah's lithium content provides yet another data point in this unresolved conundrum, potentially helping us refine our models of the early universe's chemistry. The idea that a single star could challenge so many fields, stellar astrophysics, nucleosynthesis, cosmology, dark matter, and galactic evolution, seems almost mythological. But Methuselah is very real. It burns in the sky, observable with modern telescopes, catalogued in scientific literature, and yet filled with riddles that defy easy explanation. If science is the pursuit of understanding through observation, then Methuselah is a monument to that pursuit. It teaches us that the universe still holds secrets even in its most familiar forms, like a star glowing quietly in the night sky. Its light, traveling across centuries to reach our eyes, carries within it the whispers of the ancient cosmos. And if we listen closely enough, those whispers may one day reveal truths that redefine our place in the universe. As we continue exploring the mysteries surrounding Methuselah, we must consider the broader context of stellar evolution. The star represents a link to a more primitive epoch in the universe's history. To understand its true significance, we need to revisit the fundamental processes that govern how stars are born, live, and die. Stars like Methuselah form in a much different environment compared to the stars we observe in the modern universe. In the early universe, shortly after the Big Bang, the available material for star formation was predominantly hydrogen and helium, with only trace amounts of heavier elements like carbon and oxygen. These first stars, called population 3 stars, are thought to have been massive and short-lived, burning through their fuel quickly and explosively. When they died, they left behind the elements that later formed the building blocks for future generations of stars. Methuselah, as a population 2 star, was born from a cloud of gas enriched by these early supernovae. Its composition suggests that it formed at a time when the universe was still relatively young but beginning to see more diversity in its stellar populations. This makes it one of the oldest stars we can study, offering a glimpse into a time long before our Sun or even the Milky Way galaxy itself. The fact that Methuselah is so old presents another intriguing question. How do we reconcile its ancient age with our understanding of how stars evolve? As mentioned earlier, age estimates for stars are notoriously difficult. Stellar evolution models, which predict how stars change over time, rely on complex interactions between gravity, nuclear fusion, radiation, and magnetic fields. These models are constantly being refined as new data is gathered, but there are still uncertainties in how they predict the behavior of very old stars like Methuselah. For instance, the age estimates for stars can vary depending on their metallicity, temperature, and luminosity. Stars with lower metallicities, like Methuselah, tend to evolve more slowly than metal-rich stars because their lower abundance of heavy elements means they have fewer cooling mechanisms available to regulate their internal pressure. This slows down the process of stellar evolution, meaning that a star like Methuselah could have remained in a subgiant phase for much longer than a more typical star with higher metal content. This is where the paradox of Methuselah becomes particularly pronounced. If its age is truly 14 billion years or older, it would suggest that our models of stellar evolution need significant revisions. The conventional models of stellar physics don't fully account for the long, stable lifetimes of low metallicity stars, especially those that are as massive as Methuselah. Its continued stability and longevity challenge our assumptions about the lifespan of stars. Furthermore, the presence of Methuselah raises profound questions about the evolution of galaxies. The star's high velocity and galactic halo location suggest it was not born in the Milky Way's disk but was instead part of a smaller, older galaxy that was later absorbed into our galaxy. This process, called galactic cannibalism, is a key feature of the Milky Way's growth. Over billions of years, smaller galaxies were captured and merged into our own, bringing with them their ancient stellar populations. The study of Methuselah and other stars in the galactic halo provides crucial insight into this process. By examining the motions and compositions of these stars, astronomers can piece together the history of our galaxy's formation and the role played by smaller galaxies in its evolution. Methuselah serves as a relic of the early stages of galactic formation, a living witness to the violent, chaotic history of the universe as it slowly evolved into the more stable, structured system we observe today. In a sense, Methuselah is a cosmic artifact, a relic of the early universe. Like ancient fossils that tell the story of life on Earth, Methuselah tells the story of the cosmos, of the first stars, the formation of galaxies, and the processes that shape the universe into what it is today. But Methuselah's true importance lies not only in what it has witnessed, but also in the questions it forces us to confront. It challenges our understanding of time, of the universe's age, and of the very principles that govern the birth and death of stars. As scientists continue to observe and analyze Methuselah, we may find that it holds the key to unlocking some of the most fundamental mysteries of the cosmos. It may help us understand how the first stars formed, how galaxies evolved, and how the universe itself was shaped in the aftermath of the Big Bang. Its paradoxical age may be the catalyst for new theories, new models, and new ways of thinking about the universe. But beyond its scientific significance, Methuselah also serves as a reminder of the vastness and complexity of the universe. It reminds us that there are still many unknowns, that the universe is full of surprises, and that our understanding of the cosmos is far from complete. Every time we look up at the stars, we are reminded of how little we truly know and how much there is yet to discover. In a sense, Methuselah embodies the spirit of exploration itself. It challenges us to ask questions, to dig deeper, and to push the boundaries of our knowledge. It invites us to imagine a universe much older, more complex, and more mysterious than we had ever dreamed. As we gaze upon this ancient star, we are reminded of our place in the universe, not just as observers, but as participants in a grand cosmic story that has been unfolding for billions of years. Methuselah is a testament to the beauty and complexity of the cosmos, a star that has lived longer than most of us could ever fathom, and one that continues to inspire awe and wonder in all who seek to understand the universe. And as our understanding of the universe continues to grow, perhaps one day, we will solve the mysteries surrounding stars like Methuselah. Perhaps we will find that the universe is even older than we thought, and that the secrets of time itself are far more intricate than we could have ever imagined. Until then, stars like Methuselah will continue to shine in the night sky, silently bearing witness to the cosmic drama that has played out over billions of years. They will remain, as always, our guides to the farthest reaches of time and space, urging us to look up, to wonder, and to continue the search for the answers that lie just beyond the stars. The enigma of Methuselah deepens when we consider its peculiar motion through space. Unlike the majority of stars in our galaxy that move in relatively circular orbits around the galactic center, Methuselah follows a highly elliptical and retrograde orbit, indicating that it may have originated outside the Milky Way altogether. This motion, coupled with its extreme age and low metallicity, suggests that Methuselah is not merely an old star but a true intergalactic traveler, a remnant of a smaller satellite galaxy long since consumed by our own. This is not just speculation. The Milky Way has a long history of galactic mergers. Over billions of years, it has absorbed dozens, perhaps hundreds, of smaller galaxies. Many of the stars in the galactic halo, where Methuselah resides, are believed to be the vestiges of these ancient mergers. Their chaotic orbits and varied chemical compositions contrast sharply with the ordered, metal-rich stars found in the galactic disk. Methuselah's retrograde motion, meaning it orbits in the opposite direction to most stars in the galaxy, is a telltale signature of such an origin. What makes this even more remarkable is the notion that Methuselah may have survived the turbulent process of galactic assimilation. Picture a dwarf galaxy, billions of years ago, slowly spiraling inward toward the Milky Way, its stars pulled and stretched by the immense gravity of our galaxy. Most would have been torn apart, scattered, or integrated into the growing galactic halo. But Methuselah persisted, a survivor of unimaginable cosmic upheaval, holding fast to its ancient trajectory through space and time. Its chemical makeup adds another layer to this story. Spectroscopic analyses reveal an exceptionally low abundance of heavy elements, or metals, as astronomers define them. This places Methuselah squarely among the most metal-poor stars ever observed. The lack of elements like iron, carbon, and oxygen indicates it formed very early in the universe's history, before supernovae had a chance to enrich the cosmos with these building blocks. It likely emerged in a relatively pristine environment, forged from gas only lightly contaminated by the first generation of stars. This tells us that Methuselah formed not just early, but likely in isolation or in a pocket of the universe largely untouched by the chemical evolution occurring elsewhere. The star's iron content, in particular, is about 1/200th that of the Sun. In astronomical terms, that's an extreme deficiency, supporting the idea that Methuselah's parent cloud of gas had only just begun to be enriched by previous stellar generations. In a way, Methuselah is a fossil of the pre-enriched universe, a direct link to a time when the cosmic clock had only just started ticking. Now consider the paradox again. Based on its observed characteristics, luminosity, temperature, metallicity, stellar models have consistently placed Methuselah's age at around 14.5 billion years, give or take. That's older than the universe, which is currently estimated to be 13.8 billion years old according to data from the Planck satellite and cosmic microwave background measurements. This is where the real mystery lies. How could a star be older than time itself? Scientists have tackled this problem from multiple angles. One possibility is that the uncertainties in stellar modeling are greater than previously thought, especially when it comes to very old, low-metallicity stars. By tweaking certain parameters, like the rate of energy transport within the star, the precise behavior of hydrogen fusion under such conditions, or the effects of diffusion over time, researchers can reduce Methuselah's age estimates slightly, perhaps to around 13.7 billion years. That still makes it one of the oldest stars ever recorded but places it just within the acceptable bounds of the universe's age. Another potential solution involves re-examining our measurements of the Hubble constant, the rate at which the universe is expanding. Some recent observations have hinted at inconsistencies in this value, depending on whether it's measured through the cosmic microwave background or by looking at supernovae in the local universe. If the universe is expanding faster than previously thought, that would imply a younger universe, exacerbating the Methuselah paradox. Conversely, if our models of early universe physics need tweaking, the universe might be older than we think, making Methuselah's extreme age more plausible. Then there's the question of gravitational lensing, cosmic dust, or other observational distortions that might skew our readings. Could some subtle, overlooked factor be affecting how we perceive Methuselah's brightness or temperature, thereby altering our calculations? While none of these alternatives have provided a definitive answer, they all highlight how delicate and complex these measurements are. It underscores how a single outlier, a lone star on a unique trajectory, can challenge the entire framework of cosmology. But perhaps one of the most profound implications of Methuselah is philosophical. The star forces us to confront the limits of our knowledge. Here is an object billions of years old, drifting through the void, whose very existence stretches the boundaries of our cosmic timeline. Whether or not it is older than the universe, Methuselah embodies the uncertainty that lies at the heart of science. Every model, every measurement, every theory we construct is, at best, an approximation. And sometimes, reality refuses to fit neatly within the boxes we have drawn. That's what makes Methuselah so captivating, not just its antiquity, but the humility it demands from us. It reminds us that for all our technological prowess, all our observatories and satellites and equations, the universe remains, in many ways, a mystery. Stars like Methuselah whisper to us from the deep past, telling stories in the language of light and gravity and elemental signatures. And it is up to us to listen carefully, to question relentlessly, and to never assume that we have all the answers. In the broader tapestry of the cosmos, Methuselah is a single point of light. Yet from that light, we glean profound truths about time, space, and our own origins. The atoms in our bodies were forged in stars not unlike Methuselah, ancient forges of creation scattered across the primordial universe. Every time we study such a star, we are tracing the steps that led to our existence. Imagine Methuselah, eons ago, kindling into life in a quiet corner of a nascent galaxy. Around it, the universe was still young, stars were few, and galaxies were just beginning to coalesce. It burned slowly, steadily, while the cosmos around it exploded into structure and complexity. Entire generations of stars lived and died while Methuselah continued its patient journey. Civilizations on planets billions of light years away may have risen and fallen without ever glimpsing its pale light. Yet here we are, billions of years later, pointing our telescopes toward that ancient beacon, deciphering its secrets, pondering its age, and marveling at its endurance. It's humbling. It's beautiful. It's a reminder that even in the cold void of space, there are witnesses to the history of everything. And so, Methuselah continues its orbit, a silent, unyielding reminder of the past, challenging us to rethink the very fabric of the universe. It may not have all the answers, but it certainly raises the right questions. Methuselah's tale, however, is far from over. In fact, the more closely astronomers study it, the more nuanced and perplexing its story becomes. The determination of a star's age is not a simple process. It involves careful observation, complex modeling, and a deep understanding of stellar evolution. Every element of this process is subject to uncertainties, and Methuselah sits at the intersection of many of them. Let's delve deeper into how a star's age is determined. Scientists typically rely on stellar evolution models, which are built upon our understanding of how stars change over time. These models consider a star's mass, chemical composition, and observed properties such as luminosity and temperature. They then simulate how the star evolves, from its birth in a cloud of gas to its long, slow aging as it fuses hydrogen into helium in its core. For a star like Methuselah, these models are more difficult to apply. Because it is a population 2 star, very old and metal-poor, it doesn't follow the same evolutionary track as our Sun. The lack of heavy elements significantly alters the star's energy transport mechanisms and fusion rates, requiring custom-tailored models to estimate its age. Even a small miscalculation in the input data can lead to large differences in the final age estimate. For example, a slight overestimation in brightness or underestimation in metallicity can push the modeled age beyond the current age of the universe. This is why some scientists suggest that rather than taking the Methuselah star's apparent age at face value, we should look at it as a stress test for our understanding of stellar physics and cosmology. It pushes the envelope, revealing cracks in the assumptions we've made. And that's exactly what makes it so valuable. It's not just a star, but a benchmark. Consider, for instance, the significant role played by Gaia, the European Space Agency's ambitious astrometry mission. Gaia is revolutionizing our view of the Milky Way by providing precise measurements of stellar positions, motions, and parallaxes for over 1 billion stars. For Methuselah, Gaia's data has been crucial in refining its distance from Earth, which in turn affects estimates of its luminosity, and therefore its age. Before Gaia, there was significant uncertainty in how far away Methuselah actually was. A misjudged distance means an incorrect luminosity, which skews the entire age calculation. But with Gaia's pinpoint precision, the margin of error has shrunk considerably. This alone has led to a slight reduction in the star's age estimate, helping to bring it closer to alignment with the age of the universe. Still, even the most optimistic revisions can't deny that Methuselah remains an outlier. At best, it is nearly as old as the universe itself, perhaps forming just a few 100 million years after the Big Bang. At worst, if the models are slightly off, it may indeed still sit uncomfortably older than the universe. Either way, it speaks to the possibility that our cosmological models need adjusting, or at the very least, refining. This invites us to revisit one of the biggest tools in our cosmological arsenal, the Hubble constant. Named after Edwin Hubble, the constant defines the rate at which the universe is expanding. The value of this constant is critical because it affects our estimate of the universe's age. A faster expansion rate implies a younger universe, while a slower rate suggests an older one. Traditionally, the Hubble constant has been determined in two main ways. The first is via direct measurement, by observing distant galaxies and calculating how fast they are moving away from us. This method typically produces a Hubble constant of about 73 km per second per MPC. The second method relies on observations of the cosmic microwave background radiation, the leftover glow from the Big Bang. Using this technique, the Hubble constant comes out to around 67.4 km per second per MPC. This discrepancy, often referred to as the Hubble tension, has become one of the most hotly debated issues in modern cosmology. If the higher value is correct, the universe is younger than we think, around 12.8 billion years old. This would make Methuselah appear even more anomalous. If the lower value is correct, the universe is older, closer to 13.8 billion years, bringing Methuselah more in line with known physics. But this isn't just a debate about numbers. It's a question about the very nature of reality. The tension between these values may indicate new physics, something fundamental about the universe that we haven't yet discovered. Perhaps dark energy behaves differently than we think. Maybe there's an unknown particle influencing the expansion of the universe. Or maybe there's a flaw in one of our most cherished models. In this sense, Methuselah is more than a relic, it's a beacon pointing toward a scientific revolution. And yet, for all the speculation, there's still something awe-inspiring about Methuselah's physical characteristics. It's a subgiant star, meaning it has exhausted the hydrogen in its core and is now transitioning into the next phase of its life. This is a slow, measured process for such an ancient star. Its surface temperature is around 5,500 Kelvin, and it radiates with a quiet steadiness that belies its extreme age. It is not a massive, unstable giant on the verge of collapse, nor a faint dwarf fading into obscurity. Methuselah is a survivor, resilient, enduring, and stable. Its stability is a testament to the longevity of low-mass stars. While massive stars live fast and die young, exploding in supernovae or collapsing into black holes, stars like Methuselah live slow and peaceful lives. They burn their fuel cautiously, extending their lifespan over billions of years. Methuselah's mass is estimated to be just 0.8 times that of the Sun, which explains its incredible longevity. This opens up another intriguing question: could Methuselah have had planets? And if so, could they have been ancient cradles of life? The notion may seem far-fetched, especially given the star's low metal content, which would make planet formation less likely. Heavy elements like iron, silicon, and oxygen are necessary to form terrestrial planets, and these were scarce in the early universe. Yet some studies suggest that planets can and do form around metal-poor stars, albeit with different characteristics. Perhaps Methuselah once hosted a system of primitive rocky worlds, or icy gas dwarfs. Maybe some of them were sterilized by early cosmic radiation, or maybe they were too cold and barren to ever foster life. But the idea lingers, a possibility, however remote, that life could have emerged in some form, around a star born when the universe was still young and wild. Even without planets, Methuselah's mere presence during the universe's formative years means it witnessed epochs we can only theorize about. It saw the first galaxies swirl into shape, the universe transition from opaque to transparent, and cosmic structures evolve into the vast web we see today. It is a relic not just of time, but of transition, between chaos and order, between fire and form. Its story reminds us that history is not just written in books or etched in stone. It's written in light, in spectra, in motion. Stars like Methuselah are chapters in the autobiography of the universe, composed in the language of hydrogen and helium, written across the heavens in nuclear fusion. And as we decode that language, we gain insight not only into the cosmos, but into ourselves. We are stardust, after all. The atoms that make up our bodies were forged in stars. When we look at Methuselah, we are looking at one of the oldest sources of that stardust. In a very literal sense, it is our ancestor. And yet, its future is as compelling as its past. Methuselah still burns, still glows with the steady light of fusion. Eventually, it will become a white dwarf, a dense, cooling ember that will persist for trillions of years. Long after our sun has died, long after the Milky Way has collided with Andromeda, Methuselah's remnants may still exist, slowly fading into the eternal night. It may very well outlive our entire civilization, bearing silent witness to the death of stars and the slow unraveling of time. In the vast cosmic ocean, Methuselah is a lighthouse, its steady glow guiding us not home, but backward, into the past, into the very origin of stars, galaxies, and matter itself. Methuselah's persistence defies the ordinary life cycle we assign to stars. When one thinks about the longevity of such celestial objects, the concept of time itself begins to warp. We, bound by the brevity of human life, struggle to grasp the immense scales of cosmic time. Millions and billions of years are numbers we can speak but not truly feel. Yet Methuselah embodies these numbers. It is not simply a star that has lived a long time. It is a star that has lived through all time available in the universe, nearly since the beginning. To think Methuselah may have ignited when the cosmos was still echoing with the energy of the Big Bang is to appreciate just how ancient it is. The universe, then, was a place of violent formation. Galaxies were still in their infancy, chaotic and irregular. Radiation fields were far more intense. The cosmic web, the vast structure of filaments and voids that maps the distribution of matter, was only beginning to take shape. And through it all, Methuselah burned on. What makes this all the more incredible is the fact that it survived. The early universe was not a gentle environment. Collisions between nascent galaxies were frequent. The intensity of radiation and supernovae could easily disrupt the formation of stable systems. That Methuselah still exists today, largely intact, is a cosmic miracle, a lone voyager that has traversed eons without succumbing to the ravages of space. Its orbital path adds another layer to the mystery. Methuselah is not anchored within the thin disk of the Milky Way where stars like our Sun reside. Instead, it moves in a long, elliptical orbit that takes it deep into the galactic halo and back again. This suggests that Methuselah may not have even formed in the Milky Way at all. There is a compelling hypothesis that the Methuselah Star originated in a smaller, primordial dwarf galaxy that was later cannibalized by the Milky Way during one of its many mergers. These galactic mergers were common in the early universe, and the Milky Way's halo is littered with remnants of these ancient stellar systems. Methuselah, with its extreme age and peculiar orbit, fits this narrative perfectly. It may be one of the last remaining traces of a long-vanished galaxy, absorbed and forgotten by cosmic evolution. This origin story is more than just poetic. It has implications for how we understand the growth of large galaxies like our own. If Methuselah did come from an absorbed system, it adds to the evidence that the Milky Way grew not just by internal star formation, but also by consuming smaller neighbors. This process, hierarchical galaxy formation, is central to the Lambda-CDM model, our best cosmological framework. In this sense, Methuselah's trajectory is not only a clue to its personal history but a thread in the larger fabric of galactic archaeology. As scientists dig deeper into the nature of this ancient star, they also refine their tools for investigating other celestial bodies. Methuselah acts as a benchmark, a standard against which new theories and models are tested. Every refinement in measuring its age, distance, composition, and motion sharpens our understanding of stellar evolution and the universe's timeline. One of the more exciting developments in recent years involves stellar nucleocosmochronology, a mouthful of a term that refers to using the abundances of radioactive elements within stars to estimate their ages. Just as archaeologists use carbon dating to measure the age of organic artifacts, astronomers use the decay of long-lived isotopes like thorium and uranium to date stars. This technique is incredibly precise but also incredibly challenging, as it requires high-resolution spectra and accurate models of nuclear decay rates. Methuselah, being a metal-poor star, doesn't have a strong signature of these heavy radioactive elements. But this very fact also tells us something. The lack of thorium or uranium may indicate that it formed before these elements were widely distributed in the galaxy, before the first generations of supernovae had seeded the cosmos with the products of heavy element nucleosynthesis. This would push its formation to an era when the universe was still in its chemical adolescence, just beginning to produce the heavier ingredients necessary for planets and life. Its composition is not entirely devoid of metals, however. Methuselah contains small traces of oxygen, magnesium, and silicon, light elements that suggest it was formed in the aftermath of population 3 stars. These first-generation stars, thought to be massive and short-lived, ended their lives in violent supernovae that created the first heavy elements in the universe. Methuselah may have formed from the enriched remnants of one of these early explosions, making it effectively a second-generation star. If so, it is a rare and invaluable link between the earliest stars and the more chemically complex ones that followed. This chain of stellar ancestry leads back to a time when the universe was a completely different place. The cosmic microwave background was still warm. The first proto-galaxies were only just beginning to coalesce. There were no quasars, no black holes, no heavy elements, only hydrogen, helium, and the first hints of structure. Methuselah is a fossil from this time. It doesn't just predate human history or the Earth. It predates the formation of the Milky Way as we know it. But while Methuselah's age may be its most attention-grabbing feature, its behavior as a star is equally fascinating. It is a subgiant, which means it is in a transitional phase of stellar evolution. It has stopped fusing hydrogen in its core, having exhausted its primary fuel, and is now burning hydrogen in a shell surrounding an inert helium core. This process causes the star to expand and brighten, a prelude to its eventual transformation into a red giant. This phase of life is relatively short compared to the star's main sequence lifetime, which for Methuselah was likely more than 12 billion years. In astronomical terms, Methuselah is in late middle age, approaching the twilight of its life. As it expands, it will eventually shed its outer layers into space, forming a planetary nebula. What remains will be a white dwarf, an ultra-dense core of carbon and oxygen, slowly cooling over trillions of years. These white dwarfs are among the most enduring objects in the universe. While fusion ends, the remnant will continue to radiate heat for an unimaginable span of time, eventually becoming a cold, dark black dwarf. This final form is so ancient that none yet exist. The universe simply hasn't been around long enough for any white dwarf to cool that much. But Methuselah may someday be among the first. And this raises another deep question: what will remain of us when Methuselah becomes a black dwarf? What civilizations might exist then? What stars will shine in the sky of whatever life may remain, or arise anew? Will Methuselah, now invisible and inert, still carry within it the memory of the cosmos? The idea that one star can provoke such questions is a testament to its power, not just as an astronomical object, but as a symbol. It forces us to reconcile what we think we know with what the universe is telling us. It invites us to refine our instruments, rework our models, and challenge our assumptions. It asks us to look deeper, further, and more humbly into the past. And perhaps most of all, Methuselah reminds us of how much we still have to learn. In a universe filled with billions of galaxies and trillions of stars, this one ancient light stands out, not for its brilliance or mass, but for its quiet defiance of our expectations. It is, in many ways, the most human of stars, not because it resembles us, but because it embodies our pursuit of knowledge, our awe of time, and our yearning to understand. Methuselah's story does not only unravel backwards in time, it reaches forward, echoing into the future of astronomical research and philosophical inquiry alike. Its very presence demands that we grapple with a fundamental paradox. If this star appears to be older than the universe, what does that say about the tools we use to measure time itself? This isn't just a numerical inconsistency, it's a crack in our understanding of the cosmos. And cracks, as history has shown time and time again, are where the light of revelation breaks through. At the heart of this paradox lies the age of the universe itself. The currently accepted value, based on observations of the cosmic microwave background by the Planck satellite, places the age of the universe at approximately 13.8 billion years. This measurement is derived from the lambda CDM model, lambda cold dark matter model, which is the prevailing cosmological framework describing the evolution and structure of the cosmos. According to this model, time began with the Big Bang, an initial singularity of infinite density and temperature, and since then, the universe has been expanding. This expansion is still ongoing, driven in part by a mysterious force known as dark energy. One of the key pillars of this model is the Hubble constant, which describes the rate at which galaxies are receding from us due to this cosmic expansion. However, here's where things get interesting. Different methods of measuring the Hubble constant yield slightly different values. Observations based on the early universe, such as those from the Planck satellite, give one result. Meanwhile, measurements using nearby galaxies and supernovae suggest a faster rate of expansion and thus a younger universe. This tension is known as the Hubble tension, and it has major implications for our understanding of cosmic age. If the universe is expanding faster than we think, then it may actually be younger than the 13.8 billion years estimated by Planck data. And that's where Methuselah comes in. With some early age estimates placing it at 14.5 billion years, it appears to be older than the universe itself, a cosmic impossibility, or at least an indicator that something doesn't add up. Of course, age-dating stars is a complex science. It involves modeling the internal physics of stars based on observable parameters such as luminosity, temperature, and chemical composition. Even small uncertainties in these factors can produce significant differences in estimated ages. For Methuselah, a star with unusually low metallicity and high velocity, these measurements are particularly tricky. Over the years, as stellar models have improved and distance measurements have become more precise, Methuselah's estimated age has been revised downwards slightly. Current estimates place it at about 13.2 billion years, still very old, but now within the realm of cosmic possibility. But even at 13.2 billion years, Methuselah remains one of the oldest known stars in the universe. It stands at the very threshold of stellar existence, having formed just a few 100 million years after the Big Bang. This is significant not just for its individual age, but for what it tells us about the conditions of the early universe. To understand this, consider what it takes to form a star. A cloud of gas, mostly hydrogen and helium, must collapse under its own gravity. But in the early universe, before the first stars, this gas was warm and diffuse. The first stars, known as population 3 stars, were responsible for cooling and enriching this gas with heavier elements. Methuselah, classified as a population 2 star, likely formed shortly after this first generation had gone supernova, scattering their enriched material across the cosmos. The chemical fingerprint of Methuselah supports this narrative. Its extremely low metallicity is indicative of a time before the universe had been significantly polluted by multiple generations of supernovae. It contains small amounts of elements like oxygen and magnesium, but almost no iron, suggesting it formed from a gas cloud that had been touched by just one or a few earlier stars. This makes it a living record of the early chemical evolution of the universe, an observational Rosetta Stone for the cosmic dawn. But what does it mean, truly, to be so old? Methuselah is not just a number in a database. It has orbited the galaxy dozens of times. It has passed through spiral arms filled with young stars and nebulae, likely unaffected by their drama. It has silently watched as the Milky Way grew around it, consuming smaller galaxies and forming the complex disk, halo, and bulge structures we observe today. It has endured gravitational perturbations, cosmic radiation, and the collapse of countless other stars, and yet it continues to shine. Methuselah has seen civilizations rise and fall on Earth, though from its distant perch it would not have noticed the difference. The light from its surface travels more than 190 light-years to reach us, so even the photons we receive today left the star before World War I had begun on Earth. Time for Methuselah flows in a way that makes our history feel fleeting. In the presence of such longevity, human time feels like a flicker, momentary and small. Yet for all its age and endurance, Methuselah is not immortal. Its time is limited, as is that of all stars. Eventually, the hydrogen shell around its core will also be depleted, and it will transition fully into the red giant phase. In this phase, it will expand enormously, becoming brighter and cooler on the outside even as its core contracts further and heats up. This transformation will be accompanied by mass loss, as the outer layers of the star are blown away into space, forming a planetary nebula, a beautiful, ephemeral structure of glowing gas that marks the end of stellar fusion. At its center, Methuselah will leave behind a white dwarf, a dense, Earth-sized remnant with a mass comparable to that of the Sun. These objects are supported not by fusion, but by electron degeneracy pressure, a quantum mechanical phenomenon that resists further gravitational collapse. As a white dwarf, Methuselah will no longer produce energy, but it will remain warm for trillions of years, slowly cooling and dimming. Eventually, it will become a black dwarf, a theoretical object so cold and dark that it emits no detectable light. But that fate lies far in the future, longer than the current age of the universe by a factor of hundreds. In the meantime, Methuselah serves as a unique probe into both the distant past and the far future. It teaches us not only about the universe as it was but as it will be. And it challenges us, constantly, to reconsider what we know. How do we measure time? How do we define beginnings and ends in a cosmos without boundaries? And there's a poetic symmetry to all of this. Methuselah, named after the biblical figure who lived the longest, embodies endurance in a universe defined by entropy and change. It is a symbol of persistence and resilience, an ancient flame that continues to burn in defiance of time. As we continue to study Methuselah and stars like it, we may uncover not just new insights into the age of the universe, but deeper truths about our place within it. We may learn to refine our models of stellar evolution, to reconcile discrepancies in cosmic measurements, and to develop new methods of probing the early epochs of creation. Every advancement in technology, whether it be next-generation space telescopes, more sensitive spectrographs, or improved computational models, brings us closer to unlocking the secrets that Methuselah keeps. But perhaps its greatest legacy will not be the data it gives us, but the questions it inspires. In a universe where most stars are content to fit within the limits we set, Methuselah refuses. It challenges us to look again, to measure more carefully, to think more deeply. It reminds us that for all our knowledge, we are still beginners, still finding our way in the vastness. Methuselah is a cosmic elder, a stellar witness to the birth and evolution of everything we know. And as long as it continues to shine, it will illuminate more than the space around it. It will shine a light on the enduring mysteries of the universe itself. In contemplating Methuselah, we find ourselves not only faced with questions about the star itself but about the very tools and frameworks we rely on to understand the cosmos. This one star, quiet and ancient, has rippled through every major field of astrophysics, from cosmology and galactic archaeology to quantum mechanics and the theory of relativity. To study Methuselah is to confront the boundaries of our knowledge and the assumptions that underpin them. Take for instance the issue of its trajectory. Methuselah's movement through the galaxy is not one of the circular, stable orbits we see in younger, disk-dwelling stars like our Sun. Instead, it follows a high-velocity, highly eccentric path that loops it far above and below the galactic plane. This kind of motion is typical of halo stars, remnants of an earlier phase of galactic formation when the Milky Way was still accreting mass and defining its structure. Astronomers have traced Methuselah's galactic orbit using its proper motion and radial velocity, and from that reconstructed a picture of its 200-million-year-long loop around the center of the galaxy. This path brings it through the galactic disk roughly once every 100 million years, crossing a region now filled with stars, gas clouds, and dark matter, but in its earliest crossings, perhaps to vast voids that had not yet coalesced into structure. The implications of its halo orbit are staggering. Halo stars are thought to have formed early, either within the protogalactic cloud that would become the Milky Way or in dwarf galaxies that were later absorbed by it. If Methuselah came from such a dwarf galaxy, then it may carry within its chemical makeup clues not only to the early universe but to the galactic cannibalism that shaped the Milky Way. It is a relic of an ancestral civilization of stars, many of which have long since gone dark, or been torn apart. Another extraordinary facet of Methuselah's story is its surprisingly low mass and metallicity. With about 0.8 solar masses, it is just massive enough to sustain hydrogen fusion for billions of years without exhausting its core supply too quickly. This longevity is the key to its survival. If it had been just a bit more massive, it would have burned brighter and died long ago. If it had been less massive, it might not have even ignited. Its low metallicity, particularly the paucity of iron, points to a time when supernovae were still rare and heavy elements had not yet been widely seeded into the interstellar medium. The trace elements it does possess are indicators of perhaps a single, or at most a few supernovae contributing to the material from which it formed. This sparse enrichment gives it a direct connection to the primordial nucleosynthesis of the early universe, the fusion processes that occurred in the first few minutes after the Big Bang and produced the initial abundance of hydrogen, helium, and trace amounts of lithium. Methuselah thus serves as a constraint on these early processes. It allows scientists to test models of how the first stars contributed to chemical evolution, how long it took for heavy elements to begin circulating, and how efficiently those elements were recycled into new stellar generations. Every spectrum taken from Methuselah's light, every absorption line measured in its photosphere, tells us about a time when the universe was just beginning to experiment with complexity. But even more intriguing is the philosophical gravity that Methuselah carries. Here is a star that has outlived most others. A star that began its life when the universe was still in its infancy. It has orbited the galactic core dozens of times, seen the birth of planetary systems, witnessed the collisions of galaxies, and endured countless gravitational tides and perturbations. It has seen darkness and light, entropy and order. And still, it burns. In the presence of such longevity, our own existence feels transient. We, who measure our lives in decades, cannot help but feel awe in the face of something that has seen billions of years pass. Methuselah is more than a star, it is a living timeline. A living fossil. A narrative etched in hydrogen, helium, and the sparse minerals of an early cosmos. The measurement of Methuselah's age, while now more consistent with the universe's estimated age, continues to serve as a necessary caution. Cosmology is a science of models and approximations, and no single parameter is ever truly absolute. The apparent age discrepancy taught astronomers to be more careful, more skeptical, and more precise. It forced the re-examination of data, the refinement of parallax measurements through missions like Hipparcos and Gaia, and the adjustment of stellar models to better fit what we see. In fact, the Gaia spacecraft has been pivotal in resolving some of the tensions regarding Methuselah's age. By providing highly precise distance measurements, Gaia allows astronomers to calibrate the star's intrinsic brightness far more accurately. Combined with advances in modeling stellar atmospheres and energy output, these improvements have helped reconcile Methuselah's apparent paradox, lowering its estimated age from 14.5 billion years to around 13.2 billion. Within error margins consistent with the age of the universe. Still, this reconciliation does not diminish the star's importance. It enhances it. For Methuselah has forced improvements across multiple disciplines in astronomy. It compelled refinements in cosmological constants, improved our understanding of stellar evolution, and encouraged us to look more critically at the methods by which we determine age and distance on galactic scales. Even now, scientists continue to probe Methuselah for secrets. They study its rotational velocity, its magnetic activity, and even the potential for planetary companions. While it's unlikely that Methuselah harbors planets, especially given its early formation and the scarcity of heavy elements, it is not entirely out of the question. And the implications of finding even a small planet around a star this old would be immense. It would extend the known window for planetary formation far closer to the Big Bang and suggest that the conditions for life-bearing worlds may have emerged much earlier than previously thought. The possibility, however remote, that planets formed around stars like Methuselah could reshape the search for extraterrestrial life. It would mean that the cosmic clock for life-bearing chemistry began ticking billions of years before Earth even existed. If so, then civilizations, perhaps even advanced ones, could have had head starts measured in billions of years. The cosmos could be far older, richer, and more populated than we imagine. Or it may be that life is so rare and conditions so specific that even stars like Methuselah remain forever barren. Either way, Methuselah sharpens the question, urges it forward, and places it in a wider, deeper context. It reminds us that life, time, and consciousness are not guaranteed. They are emergent properties of a chaotic universe. They are precious, fragile, and possibly rare. But there is another lesson too, a more hopeful one. Methuselah has endured. Through collisions, gravitational disturbances, stellar flybys, and the changing tides of galactic evolution, it has remained intact. It has burned steadily, its nuclear heart converting hydrogen to helium, one atom at a time, for more than 13 billion years. In a universe defined by impermanence, this is a profound form of stability. A reminder that some things, perhaps the most vital things, can endure. And if a star can do that, what might we accomplish, with our minds, our telescopes, and our curiosity? If Methuselah is a cosmic elder, then perhaps we are its inheritors. Its watchers. The minds that seek to understand what it has witnessed. Methuselah, the star that nearly broke cosmology, has instead become its quiet guardian, still glowing, still moving, still challenging us to know more. Methuselah's continuing presence within our night sky also serves a unique purpose. It acts as an intergenerational message across time. This star is not simply an astronomical object, but a kind of living document, a beacon whose light has encoded the unfolding story of the cosmos. Long before human beings evolved, before Earth took form in a dusty protoplanetary disk, before the sun ignited in a glowing nebula, Methuselah had already been burning for billions of years. Its light has bathed countless celestial regions and passed by innumerable cosmic events, acting as a silent witness to the birth and death of galaxies, stars, and potentially civilizations. As observers on a tiny planet orbiting an unremarkable star, we look up at Methuselah and tap into that profound continuity. It is an anchor in a sea of astronomical change, a fixed point of comparison when everything else in the cosmos is moving, transforming, or vanishing. And because it's relatively close to us, approximately 190 light-years away, it serves as a kind of calibration tool for the early history of our universe, sitting right within our local neighborhood but tied to the distant, ancient past. We cannot ignore the poetic irony here. That a star dubbed Methuselah, named after the biblical patriarch known for his extreme longevity, would live long enough to challenge the very idea of cosmic time. It's as if nature conspired to create a symbol, wrapped in hydrogen and helium, that would provoke human beings to rethink everything they thought they knew about creation. For many decades, the tension between Methuselah's age and the estimated age of the universe sent shockwaves through the astrophysical community. At its most controversial, the star appeared to be older than the universe itself, a clear impossibility that hinted at deep misunderstandings in either stellar evolution, cosmological parameters, or both. This paradox ignited fierce debates and drew global attention from scientists eager to resolve it. Early measurements from the Hipparcos satellite placed Methuselah at an age of about 14.5 billion years, which was unsettling given that the cosmic microwave background, measured by the Wilkinson Microwave Anisotropy Probe, WMAP, suggested the universe was about 13.7 billion years old. How could a star be older than the very spacetime that created it? This was not just a small discrepancy. It was a profound challenge to the foundations of modern cosmology. If true, it would mean that one of the pillars of our understanding, namely the age of the universe, was flawed. Either that or the star's age estimation was off, which in turn would suggest serious flaws in our stellar evolution models. Researchers had to ask, are we miscalculating the rates at which stars consume their nuclear fuel? Are we misunderstanding the effects of metallicity, opacity, or convection in aging stars? These questions drove a flurry of scientific research. Every parameter related to Methuselah was scrutinized. Astronomers studied its temperature, luminosity, radius, and parallax with increasingly advanced tools, eventually culminating in more accurate distance measurements from the Gaia Space Observatory. With each refinement, the age estimation was nudged downward, and the margin of error tightened. Today, Methuselah's age is thought to be around 13.2 billion years, which places it within the estimated 13.8 billion year age of the universe, barely, but within the margin of consistency. This resolution, however, doesn't diminish the importance of the mystery. In fact, it elevated Methuselah to a new status, not as an error or an outlier, but as a keystone in understanding the evolution of the cosmos. Its continued existence acts as a living validation of our most fundamental theories. It's a check against the assumptions we make in the deep study of space-time, matter, and energy. And it opens a door to another incredible concept, the formation of the first stars in the universe. Known as population 3 stars, the first generation of stars formed after the Big Bang were composed almost entirely of hydrogen and helium, with virtually no heavier elements. These stars were likely extremely massive, short-lived, and responsible for seeding the early universe with the first traces of carbon, oxygen, and iron through supernova explosions. However, none of these primordial population 3 stars have ever been directly observed. They've long since died, and their remnants are too diffuse or distant to detect. Methuselah, on the other hand, is a population 2 star, a second-generation object formed shortly after those first stars exploded and recycled their material into new stellar nurseries. It contains trace amounts of heavier elements, or metals, as astronomers call them, but at levels so low that its very composition serves as a fossilized record of early cosmic conditions. It is from stars like Methuselah that we can begin to reconstruct the chemical evolution of the universe. By measuring its elemental makeup, particularly its iron-to-hydrogen ratio, we can estimate how many previous generations of stars existed before it. The very presence of a single element beyond helium in its atmosphere is a clue about the earliest supernovae, suggesting they had already begun to seed the cosmos with the building blocks of future worlds. Thus, Methuselah provides not just a window into the past, but a way to reach back through time and infer the behavior of stars we will never see. It acts as an indirect probe of the population 3 epoch, a time that otherwise remains hidden in darkness, long before galaxies fully assembled or quasars lit up the sky. From this perspective, Methuselah is more than a challenge to cosmological models. It is a precious artifact, a remaining thread from the cosmic dawn. And its value extends far beyond age estimations. It contributes to our understanding of nucleosynthesis, the birth of heavy elements, the physics of stellar interiors, the gravitational structure of the galaxy, and the life cycle of stars. In many ways, Methuselah's story parallels humanity's own scientific journey. What began as a mysterious anomaly has grown into a profound source of insight. What once threatened our models has instead improved them. It serves as an emblem of humility, a reminder that nature always knows more than we do, and that our duty is not to force answers, but to refine the questions. Perhaps the most stirring aspect of Methuselah is the realization that it is still here, still burning, still observable. While many stars far younger than it have gone supernova, collapsed into white dwarfs, or been absorbed by black holes, Methuselah remains intact. That longevity is not merely an outcome of its initial mass or chemical composition. It is a testament to the delicate balance that allows stars to live for billions of years. And in that balance, we see not just astrophysics, but art. The art of the cosmos arranging atoms into forms that radiate for eons. That light, streaming from its outer layers, traveling through space at 186,000 miles per second, eventually reaches our telescopes and detectors. When we collect it, split it through a spectrograph, and analyze its fingerprints, we are performing something like cosmic archaeology. We are digging through ancient light, deciphering the messages embedded in its patterns, and learning not just about the star, but about the universe that gave rise to it. And though Methuselah may one day fade, perhaps collapsing into a white dwarf or slowly shedding its outer layers into a planetary nebula, its story will remain. Not just as data in scientific archives, but as an enduring part of our species' exploration of the cosmos. In every great journey, there are milestones, signposts that mark our progress and guide our understanding. Methuselah is one such milestone. A star older than most things in the universe. A survivor from a forgotten age. A reminder that time, though vast and unyielding, can also be a source of wonder. As we continue our journey through the enigma of the Methuselah Star, we must consider the broader implications of its existence on our understanding of cosmic structure. A single star cannot be isolated from the grand narrative of the galaxy that contains it. Methuselah orbits within the Milky Way, but its path is far from typical. Unlike stars nestled in the galactic disk with relatively circular and stable orbits, Methuselah travels through a highly elliptical orbit that takes it far above and below the galactic plane. This trajectory tells a story, a dynamic one, shaped by ancient gravitational interactions and possibly even galactic mergers. Such orbits are characteristic of halo stars, and Methuselah's placement in the galactic halo is an important clue about its origin. Halo stars are typically old, metal-poor, and often exhibit retrograde orbits, meaning they orbit in the opposite direction of the galactic disk's rotation. This strange path hints that Methuselah may not have formed within the Milky Way at all. Instead, it may be a relic of a smaller dwarf galaxy, long since devoured by our own. This raises an astonishing possibility. Methuselah could be an intergalactic immigrant, a survivor of cosmic assimilation. Long ago, before the Milky Way had grown to its present size, it likely absorbed smaller galaxies in a process known as hierarchical formation. The debris of those galaxies, stars, gas, and dark matter, were stretched and mixed into the growing halo. Methuselah could be one of these survivors, bearing the chemical and dynamic signature of a long-lost stellar population. Its path through space, then, is not just a function of gravity. It's a scar of galactic history, a trace left by a cosmic collision that occurred before human beings had language, before Earth even existed. And as we track Methuselah's motion with exquisite precision using the Gaia satellite, we can map this history in stunning detail. Gaia's astrometric measurements, tiny shifts in a star's position against the background sky, allow us to reconstruct Methuselah's orbit over millions of years, providing a kind of celestial archaeology. This orbit reveals other wonders, too. It suggests that Methuselah spends much of its time in regions of the galaxy where star formation is rare and interstellar material is sparse. In these isolated domains, Methuselah has aged undisturbed, avoiding close encounters that might strip away its outer layers or alter its composition. The star's longevity, then, is not just a function of its mass or metallicity, it's also a product of its serene, solitary journey through the galactic outskirts. Yet, its metal-poor nature is itself a defining aspect. To astronomers, metals refer to any element heavier than helium. Methuselah contains only trace amounts of these elements, indicating it was formed before many generations of stars had enriched the interstellar medium with the heavy elements forged in their cores. This low metallicity means it is a second-generation star, but formed so soon after the first generation that it retained a primordial purity, almost untouched by cosmic recycling. This is critical for understanding galactic chemical evolution. When stars form, they inherit the elemental makeup of their natal clouds. As stars age and die, they return newly forged elements into space through winds, supernovae, and other processes. Over time, this causes a gradual buildup of heavy elements in the galaxy. The composition of stars like Methuselah, then, acts as a probe into an early stage of this process, a fossil that preserves the conditions of its birth cloud. More intriguingly, Methuselah's lack of metals has consequences for its internal physics. Metal-poor stars behave differently than metal-rich ones. They are hotter, bluer, and more compact for a given mass. Their fusion rates are subtly different, and their opacity, their ability to trap heat, is altered. This affects how they evolve, how long they live, and even what elements they can produce. Understanding stars like Methuselah helps calibrate models for a class of stars that dominated the early universe. And herein lies another layer of mystery. Could Methuselah itself host planets? While early theories posited that metal-poor stars couldn't form planetary systems, since metals are essential for forming rocky worlds, this idea has since been challenged. Recent exoplanet discoveries around metal-poor stars suggest that planet formation may be more robust than previously thought. If Methuselah ever formed planets, they would be ancient beyond comprehension, potentially over 13 billion years old. Any hypothetical worlds orbiting it would have had a head start on evolution by billions of years. The implications are staggering. Could such a system harbor ancient life? Could it bear evidence of alien civilizations so old that they predate humanity's evolutionary ancestors by eons? We have no evidence of such planets around Methuselah, but the possibility remains a tantalizing question. If we could detect them, they would instantly become targets of immense scientific interest. They would be the oldest potentially habitable environments ever discovered, time capsules containing the biological and chemical history of a primordial universe. Even without planets, Methuselah offers clues about the structure and shape of the early Milky Way. Its chemical fingerprint, the abundance ratios of elements like magnesium, calcium, and titanium, can be compared to other halo stars to identify shared origins. This technique, known as chemical tagging, allows astronomers to group stars into ancient associations, tracing them back to the stellar nurseries from which they emerged. In some cases, these groups can be linked to now destroyed dwarf galaxies or globular clusters. If Methuselah shares its chemical signature with others, we might identify its siblings, stars formed in the same ancient cloud, long since scattered across the sky. These sibling stars could further constrain our models of early galaxy assembly, offering a more complete picture of the chaotic, violent youth of the Milky Way. But despite its great age, Methuselah is still in the subgiant phase of its evolution. It has burned hydrogen in its core for billions of years, producing energy through nuclear fusion and resisting the crush of gravity. Now, as its core hydrogen depletes, it is beginning the slow transformation into a red giant. The outer layers are expanding, the fusion process is shifting, and the star is entering its final evolutionary stages. Eventually, Methuselah will become a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. In that form, it will no longer undergo fusion. It will shine only by residual heat, slowly cooling over trillions of years. In fact, the white dwarf stage is effectively eternal by human standards. It is possible that Methuselah, as a white dwarf, will outlast every star currently burning in the Milky Way. This is the final irony. A star born in the aftermath of the Big Bang will survive long after our sun dies. It will persist into a future so remote it defies imagination, a universe of red dwarfs, black holes, and ever-expanding emptiness. Methuselah's second life, as a white dwarf, will continue in a cosmos growing colder, darker, and lonelier. And yet we know it. We see it. We study it. We, a civilization that appeared only moments ago in cosmic terms, have reached into the sky and pulled from it a story that spans the life of the universe. From a small planet in an unassuming solar system, we have identified a relic from the dawn of time, deciphered its composition, mapped its orbit, and puzzled over its age. This is one of the greatest achievements of the human spirit, the ability to connect to something so vast, so ancient, and so fundamentally different, yet still find meaning in it. Methuselah is not just a star. It is a mirror. A mirror in which we see our quest for knowledge reflected. A cosmic elder whose light travels across time not merely to illuminate space, but to illuminate the questions burning in the hearts of those who watch the sky and wonder where it all began. And so we look deeper, not just at Methuselah's light, but at what that light carries across eons. Every photon emitted by the star holds a record of its internal conditions. By studying the spectrum of that light, we peel back the layers of its life. Spectroscopy reveals the fingerprint of elements in the star's atmosphere. The sharp absorption lines carved into the spectrum correspond to elements like iron, oxygen, and lithium. These lines are not just identifiers. They are time capsules, records of chemical processes billions of years old. Methuselah's spectrum tells us it is iron poor, with only about 1/250th the iron content of our Sun. This deficiency is not due to the star burning through its iron. Iron is not a fuel in stellar fusion, but because the gas cloud from which Methuselah formed was itself nearly devoid of heavy elements. This means that at the time of Methuselah's birth, few massive stars had yet lived and died to enrich the cosmos with supernova debris. The implication is profound. Methuselah formed before the galaxy was chemically mature, before elements necessary for life as we know it were widely distributed. But there is more. By analyzing not just the presence of elements but the ratios between them, particularly alpha elements like magnesium and calcium compared to iron, we gain insight into the type of supernovae that seeded the gas cloud Methuselah formed from. High alpha-to-iron ratios suggest that the gas was enriched primarily by Type II supernovae, the explosive deaths of massive stars. This aligns with a very early formation time, before Type I supernovae, which take longer to occur, could contribute significant iron. So now we can place Methuselah in a cosmological timeline. Born from a gas cloud seeded by the first massive stars, before low-mass stars had time to die and recycle their material, it represents a direct descendant of the universe's first metal-generating processes. This makes it not just an old star, but one of the most informative tracers of early cosmic chemistry we have ever encountered. Yet, the conundrum remains. Methuselah's age, as estimated by stellar evolution models, was once calculated at 14.5 billion years, significantly older than the universe itself, which is 13.8 billion years old. While later refinements reduced that estimate to around 13.2 billion years, the initial discrepancy forced astronomers to reevaluate their models. Was our understanding of star evolution flawed? Or was the age of the universe miscalculated? To address these questions, scientists scrutinized every aspect of the models used to estimate stellar ages. These models rely on inputs such as luminosity, temperature, metallicity, and mass. Even a small change in assumed metallicity can shift the age estimate by hundreds of millions of years. Similarly, assumptions about nuclear reaction rates, helium abundance, or convective mixing can skew the timeline. Methuselah forced astronomers to fine-tune their parameters with greater precision than ever before, pushing the boundaries of computational astrophysics. One major improvement came from the Hubble Space Telescope. Using parallax measurements, small shifts in the star's apparent position against more distant background stars as Earth orbits the Sun, astronomers were able to more accurately determine Methuselah's distance. This, in turn, allowed for a more precise luminosity estimate, a crucial variable in age modeling. The improved distance reduced the star's estimated age to a range more consistent with the age of the universe, resolving, for the most part, the paradox. However, some uncertainty still lingers. The margin of error is large enough that the age of Methuselah still presses against the edge of the universe's timeline. This tension may yet point to gaps in our understanding of the cosmos. Perhaps our assumptions about the early universe, or even the nature of time and cosmic expansion, require revision. The Methuselah Star thus becomes a keystone in both galactic archaeology and cosmology. It offers constraints on dark energy models, inflationary theory, and the physics of the early universe. It reminds us that even a single anomaly can drive scientific advancement, forcing us to question, refine, and rebuild our theories. The idea that a single star can influence so many disciplines is both humbling and exhilarating. Methuselah bridges the gap between stellar astrophysics, nuclear physics, galactic evolution, and cosmology. It's a nexus point where multiple scientific paths converge. And perhaps, most intriguingly, it's a reminder of how much we don't yet know. We must also consider the philosophical dimensions of such an ancient entity. For all of human history, civilizations have looked to the stars with awe and wonder. But Methuselah transcends myth. It has witnessed epochs no human mind can fully comprehend. When Methuselah was born, there were no planets in our solar system. There were no galaxies in their current forms. The entire visible universe was a fraction of its current size. This lends the star a kind of quiet majesty. It is not just a celestial object, it is a survivor. It has endured the shifting tides of gravity, the chaos of galactic mergers, the birth and death of stars all around it. It has seen galaxies collide, quasars blaze and fade, black holes merge, and solar systems rise and fall. And through it all, it has continued to burn, steadily and patiently, a sentinel of time itself. What does this mean for us? Why do we care about the age of a distant star? Because understanding Methuselah helps us understand ourselves. The universe is our origin story, and every star like Methuselah is a chapter in that story. If we can read these chapters, we begin to grasp the full narrative, from the primordial hydrogen clouds to the emergence of consciousness. We begin to see ourselves not as isolated beings on a small blue planet, but as participants in a cosmic evolution stretching back billions of years. The study of Methuselah also inspires new questions. Are there even older stars we have yet to discover? Are there first-generation stars, the so-called population 3 stars, still out there, hiding in the galactic halo or in distant dwarf galaxies? These hypothetical stars, made almost entirely of hydrogen and helium, have never been observed. But Methuselah, as a second-generation star, hints at their prior existence. Finding a true population 3 star would be like finding the holy grail of astronomy, direct evidence of the universe's first attempt at star-making. Methuselah, then, is not just a subject of study. It is a guide. It leads us toward questions more profound than any answers we currently possess. And as we develop new telescopes, like the James Webb Space Telescope, or the upcoming Extremely Large Telescope, we gain tools to follow that guide deeper into the cosmic past. The Methuselah Star teaches us to be patient, to be humble, and to be curious. It reminds us that the universe is old, vast, and mysterious, but also intelligible. That we can, with effort and imagination, pull back the curtain on time itself, and catch a glimpse of what came before everything we know. Methuselah stands not only as a relic but also as a compass, pointing us toward a deeper understanding of where we came from and how everything we see around us began. One of the most fascinating aspects of this stellar enigma is its trajectory through space. The Methuselah Star doesn't merely orbit the center of the Milky Way like the Sun or many other stars in the galactic disk. Instead, it follows an eccentric, elliptical orbit that takes it far above and below the galactic plane, suggesting that it is part of the Milky Way's stellar halo. This highly elongated orbit means that Methuselah plunges through the galactic disk at great speeds, like a cosmic wanderer on a never-ending loop through the galaxy's vast reaches. This motion has significant implications. Stars that follow such orbits are often some of the oldest objects in the Milky Way. Their motion suggests they formed before the galaxy had fully coalesced into a spiral structure. In fact, it's plausible that Methuselah formed outside the Milky Way entirely. Some astronomers propose that it may have originated in a small dwarf galaxy long ago absorbed by the Milky Way's growing gravitational pull, a common process in galactic evolution known as hierarchical merging. If so, Methuselah is a refugee from another galaxy, now caught in a gravitational embrace it cannot escape. To trace this motion, astronomers rely on precise astrometric data, information about the star's position, velocity, and distance. With missions like Gaia, we've been able to chart its orbit in 3 dimensions, reconstructing not only where Methuselah is now but where it has been and where it is going. Over the course of hundreds of millions of years, Methuselah arcs in and out of the galactic plane, a journey that spans thousands of light years. Its velocity relative to the Sun is high, another indicator of its halo star status. And every pass through the disk sees it weaving through swarms of younger stars, like an ancient ghost gliding through a sea of youth. But there is more to uncover than just the star's path. Consider the physical conditions of the universe at the time Methuselah formed. This was an era of darkness, literally. The universe had emerged from the cosmic dark ages, a period after the Big Bang when neutral hydrogen filled the cosmos and no stars yet shone. When the first stars formed, they initiated the process of reionization, transforming the universe's opaque fog into a transparent expanse. Methuselah, being among the second generation of stars, likely emerged just after this cosmic transformation, in an epoch that bridged the dark past with the luminous future. Imagine the conditions in that primordial gas cloud, nearly devoid of metals, turbulent from gravitational collapse, bathed in the faint glow of a still young universe. The pressure, temperature, and density conditions had to be just right for a star like Methuselah to form and sustain a long, stable existence. The processes that governed its birth are the same processes that gave rise to countless stars afterward. But unlike those stars, Methuselah has endured. Its endurance is also rooted in its mass. Methuselah is a low-mass star, roughly 0.8 times the mass of the Sun. This is a crucial detail. Low-mass stars burn their fuel slowly, living for billions, even trillions of years. In contrast, massive stars die quickly in spectacular supernova explosions. Because Methuselah was born with a small mass, it has eked out its energy over a vast span of time, like a candle burning low and long. But its mass alone is not enough to ensure such longevity. Internal processes within the star, like convective mixing and the efficiency of hydrogen fusion, also play a role. In Methuselah's case, the near absence of metals affects how energy moves through the star. Metal-poor stars transport energy differently than metal-rich stars, with implications for their brightness, size, and lifespan. These differences must be modeled with extraordinary precision to arrive at accurate age estimates, and even small errors can lead to massive discrepancies. The story of Methuselah also intersects with our understanding of nucleosynthesis, the creation of elements within stars. Although Methuselah itself is not responsible for producing large amounts of heavy elements, its very existence provides clues about the chemical history of the cosmos. The ratios of light elements in its atmosphere, such as lithium and beryllium, can offer insights into the processes that occurred in the earliest generations of stars. For example, the observed abundance of lithium in old stars like Methuselah is lower than predicted by Big Bang nucleosynthesis models, a puzzle known as the cosmological lithium problem. Methuselah contributes to this puzzle, adding one more layer to the complex and still unfinished tapestry of cosmic evolution. As we zoom out from Methuselah's surface and trajectory, we must consider its role in broader cosmological debates. One of the reasons Methuselah generated such excitement and controversy is because its estimated age came so close to, or even exceeded, the age of the universe. According to the standard cosmological model, the universe is about 13.8 billion years old, a figure derived from observations of the cosmic microwave background radiation and the expansion rate of the universe, known as the Hubble constant. But the Hubble constant itself is the subject of ongoing debate. Different methods of measuring it yield different results. Local measurements, using supernovae and Cepheid variables, tend to give a slightly higher value than measurements based on the cosmic microwave background. This discrepancy, known as the Hubble tension, has become one of the most significant unresolved issues in modern cosmology. And Methuselah sits right in the middle of it. If the universe is younger than some local measurements suggest, and if stars like Methuselah are older than expected, then we may need to rethink one or both sets of data. Are our stellar evolution models off? Is the cosmic microwave background telling the full story? Or could new physics, such as interactions with dark energy, modified gravity, or extra dimensions, be required to resolve the tension? Methuselah doesn't give us direct answers, but it provides a critical data point. It challenges us to test our assumptions, refine our models, and explore alternative explanations. In this way, it serves as both a beacon and a barrier, a light that guides and a mystery that resists. But Methuselah's relevance doesn't end with astrophysicists and cosmologists. It has the power to inspire everyone. Consider what it means for a single star to have endured for nearly the entire lifetime of the universe. It has existed without interruption through cosmic epochs, each one marked by profound changes. When Methuselah formed, there were no galaxies in their current shapes, no solar systems like ours, no planets with sentient beings looking back at the stars. It has orbited through galactic storms, outlived generations of stars, and watched from afar as new systems blossomed into being. It is a cosmic time capsule, not of human history, but of universal history. Its existence reminds us that time stretches far beyond our own lifespans, that the story of the cosmos is still being written, and that we, however briefly, are part of that story. And so, the Methuselah Star endures, not merely as an astrophysical object, but as a symbol of cosmic persistence. It exists in a realm far removed from our everyday experiences, yet it shapes our understanding of everything. Its paradoxical age, its ancient chemical fingerprint, its sweeping galactic journey, all these elements combine to form a portrait not only of a star, but of a universe still unfolding its secrets. Yet as we deepen our understanding of the Methuselah Star, we realize how it challenges not just our models of cosmology or stellar evolution, but the very framework of how we determine the past. In science, the past is not just remembered, it is measured, extrapolated, and simulated using data and theory. But Methuselah sits at the edge of those measurements, blurring the line between what we think we know and what we must accept we may not. It is, in many ways, a mirror, reflecting both our achievements and our ignorance. And that ignorance is not a flaw, it's the fuel for discovery. Methuselah's puzzling age estimate, once believed to be older than the universe itself, forced astronomers to revisit their assumptions. They reanalyzed parallax data, scrutinized chemical abundances, and refined stellar evolution codes. They reevaluated distance measurements, atmospheric models, and even the underlying physics of fusion processes. The effort to resolve the star's age was not merely a correction, it was a collective act of sharpening the blade of science. As of the most refined estimates, Methuselah is now thought to be about 14.27 billion years old, with a margin of error that brings it into slight alignment with the age of the universe at 13.8 billion years. This overlap, however, is not a comfortable reconciliation. It's a tense compromise. The star may not be older than the universe after all, but it certainly presses hard against the universe's upper limit. And that pressure, metaphorically speaking, could rupture if even one piece of the cosmic puzzle is misaligned. The concept of age in astronomy is itself a slippery term. For humans, age is straightforward, measured from birth to the present. For stars, it's an inferential process derived not from direct observation, but from complex calculations involving mass, luminosity, chemical composition, and models of nuclear fusion. A star's age is a story told backward, built on predictions of how stars evolve over billions of years. Change one part of the story, say, the assumed opacity of stellar plasma, and the conclusion changes too. This is why Methuselah's age, despite recent recalculations, remains subject to revision. It's also why it continues to spark curiosity across the global scientific community. Let's also consider the philosophical implications. If the universe is 13.8 billion years old, and Methuselah is nearly as old, that means this single object has seen nearly everything the cosmos has experienced. It predates our solar system, which formed a mere 4.6 billion years ago. It predates Earth, predates life, predates the galaxies in their current shapes. Methuselah is a survivor from a time so long ago it defies our ability to truly conceptualize it. Imagine a timeline of cosmic events. The Big Bang occurs. The first atoms form. The universe cools and darkens. Stars ignite, galaxies form, dark energy begins accelerating the universe's expansion. Amidst this cosmic storm, Methuselah is born, steady and silent. And while stars have flared and died, galaxies have collided and reformed, and black holes have devoured untold masses of matter, Methuselah has endured, emitting a steady glow through eons. The entirety of human civilization, our cultures, wars, art, science, and dreams, occupy not even a blink in Methuselah's timeline. We often look at ancient artifacts, monuments, fossils, scrolls, with reverence, because they connect us to a past we did not live but still feel bound to. Methuselah is like that, but on a universal scale. It's a monument to a time before memory, before record, before even the structures we rely on to frame the universe. And yet it continues to shine. The starlight from Methuselah carries information across the void. Every photon it emits is like a messenger, telling us about the internal temperatures of its core, the elements in its atmosphere, the pressure and density gradients under its surface. These photons travel through space until they reach our telescopes, instruments meticulously designed to decode their message. That message doesn't arrive in words, but in wavelengths, spectral lines that scientists translate into the language of atomic transitions and stellar physics. This is where spectroscopy comes into play, one of the most powerful tools in astronomy. By breaking down Methuselah's light into its component wavelengths, scientists can detect the fingerprints of elements like hydrogen, helium, iron, and more. These fingerprints are more than mere identifiers, they are timestamps. The absence or scarcity of heavy elements in the spectrum confirms that the star formed before those elements were widespread, which aligns with an early formation era, consistent with its ancient status. Yet for all its quietness, Methuselah participates in a universe that is anything but static. Even now, it continues its orbit through the galaxy. It moves in a halo, a roughly spherical distribution of stars surrounding the Milky Way. This is not a region of dense star formation like the spiral arms. It is a region filled with old, metal-poor stars, ancient relics of the galaxy's youth. Methuselah is one among many such halo stars, but its proximity and measurable parameters make it the most celebrated. The existence of such a halo tells us something about the Milky Way's formation. It suggests a chaotic origin, one marked by mergers, tidal streams, and gravitational interactions. Dwarf galaxies once collided with what became the Milky Way, their stars dispersed and blended into the halo. Methuselah may be a fossil from such a merger. Its motion through space, unlike the orderly rotation of disk stars, resembles the erratic paths of stars that were gravitationally captured rather than formed in place. We must also talk about how this story affects our understanding of the early universe itself. Every time we confront a data point like Methuselah, we are forced to revisit our cosmological assumptions. Did the early universe cool and clump more rapidly than we thought? Were stars forming even earlier than the earliest visible galaxies? Were there periods of star formation we've yet to detect? Future telescopes like the James Webb Space Telescope, already operational, and its successors may eventually reveal galaxies even older than our current record holders. But a star like Methuselah, existing in our own galactic neighborhood, provides a complementary lens, a nearby window into the faraway past. It is the closest far thing, a relic from a time long before local space filled with the newer stars that now illuminate our skies. And we cannot ignore how this intersects with the study of dark matter and dark energy, two of the most confounding elements of our universe. The motion of stars like Methuselah helps astrophysicists map the gravitational potential of the Milky Way. Because the star is not bound to the galactic plane, it samples the three-dimensional gravitational field of the galaxy, offering clues about the distribution of unseen mass. Methuselah's trajectory is like a probe, moving through space and telling us about what lies unseen, whether that be the ghostly dark matter halo that envelopes our galaxy or the overall mass density of the local galactic environment. In this way, Methuselah is more than just a star, it's an instrument, a tool, a participant in the great experiment of cosmic history. It continues to orbit. It continues to emit light. It continues to challenge and inspire us, compelling us to ask deeper questions about the nature of time, the structure of matter, and the ultimate origins of the universe. Methuselah's continued presence in the galactic halo underscores a profound cosmic patience. For more than 14 billion years, it has remained relatively unchanged in structure, its internal processes unfolding at a slow, steady pace. This longevity is due in part to its mass, lower than that of the Sun, and to its low metallicity. Stars with low metal content generally burn their fuel more slowly than their more metal-rich counterparts. And so, while massive stars live fast and die young in explosive supernovae, stars like Methuselah endure, aging gracefully in the quiet void of space. This notion, that longevity is intertwined with simplicity, has philosophical depth. In human terms, it's akin to the idea that minimalist lifestyles often lead to greater sustainability. Methuselah, stripped of the heavy elements that adorn younger stars, reflects this principle on a stellar scale. It teaches us that enduring structures can emerge not from complexity, but from the purity of simplicity. Its hydrogen and helium, forged in the Big Bang, remain the main ingredients of its being, untainted by the elaborate periodic table that later cosmic events brought into abundance. The star's light, though faint compared to closer or younger stars, is nonetheless detectable and measurable with great precision. And each measurement reveals yet more layers of mystery. One particularly fascinating measurement comes from astroseismology, the study of stellar oscillations. These oscillations, like the ringing of a bell, provide insights into a star's internal structure. By analyzing these patterns, astronomers can infer details about the star's core, its temperature gradients, and even its past evolutionary phases. While Methuselah is not the ideal candidate for full astroseismic study due to its distance and brightness, even partial data can help anchor stellar evolution models, especially for population II stars, ancient stars formed before the galaxy was chemically enriched. Methuselah, as the population 2 star is part of a classification that spans thousands of known stars, each a relic of a time before the universe became crowded with the heavier elements we see today. These stars are sparse in metallicity but rich in historical value. Studying their behavior, chemical makeup, and distribution within the galaxy allows us to reconstruct the history of the Milky Way. They're like archaeological layers and rock formations, each one telling a story of galactic growth, merger, and transformation. In Methuselah's case, the story it tells is particularly sharp. Its path through space is not circular like stars in the disk of the Milky Way. Instead, it follows a highly elliptical orbit that takes it high above and below the galactic plane. This behavior further supports the idea that it may have originated from a different part of the galaxy, or even from another galaxy entirely, before being gravitationally captured. It is a stellar immigrant, whose journey is mapped in the sky across millions of years. Such migration raises deep questions about the early dynamics of the Milky Way. What kinds of gravitational interactions occurred to fling Methuselah into such a wide orbit? Was it ejected from a denser star-forming region due to a close stellar encounter or gravitational slingshot? Was it pulled into the Milky Way's halo as part of a cannibalized dwarf galaxy, long since absorbed into our own? These are not idle speculations. They are the very questions astrophysicists model using massive cosmological simulations. Supercomputers render the evolution of galaxies over billions of years, tracking the dance of stars and dark matter, the birth and death of suns, and the flows of interstellar gas. In many of these simulations, stars like Methuselah appear not as outliers, but as expected artifacts, proof that galaxies like the Milky Way grew through violent, complex, hierarchical processes. And yet, Methuselah's mystery goes beyond mechanics. It forces us to revisit the timeline of cosmic history. If it formed just 200 million years after the Big Bang, that means the first stars had already exploded as supernovae, seeding the universe with heavier elements and triggering the birth of second-generation stars. This pushes back the formation of the first galaxies, perhaps even into the first 100 million years of cosmic time. It compresses the early universe's evolutionary timeline and demands that we understand how such rapid transformation could have occurred. Theoretical models must then account for faster cooling of primordial gas clouds, more efficient star formation, and possibly even exotic physics that accelerated the condensation of matter. Some cosmologists speculate that dark matter may have played a more active role in these early epochs, not just providing gravitational scaffolding but also influencing how baryonic matter, normal matter, clumped and cooled. In that sense, Methuselah is not just a window into the past, it is a test case for fundamental cosmological theory. Yet for all its cosmic implications, Methuselah also possesses a kind of stark, poetic solitude. It has outlived billions of other stars. It existed before the Earth, before the Sun, before even our galaxy's current spiral shape was fully formed. While solar systems have formed and vanished, while black holes have swallowed the remains of supernovae, Methuselah has persisted. Its solitude is not one of sadness, but of witness. It stands as a lone survivor, a time traveler with no need to move through time, because time moves through it. When you look up into the night sky, you're not seeing the present. You're seeing the past, because light takes time to travel. With Methuselah, that truth deepens. You're not just looking into the past, you're looking into the deep past, into an age when the cosmic microwave background had only just cooled enough to allow hydrogen to form, when the universe was still dim and filled with primordial darkness. You're seeing something so ancient, so persistently luminous, that it seems almost miraculous. And here on Earth, we marvel at this star through the lenses of telescopes and the algorithms of data processing. We decode its story using science, but we also feel its story in our bones. Methuselah reminds us that the universe is not just vast in space, but in time. It reminds us that even in the silence of deep time, there can be continuity. There can be light. There can be presence. Methuselah's quiet presence in the halo of the Milky Way is not simply a relic of a past era. It is a thread that binds the present cosmos to the dawn of creation. Every spectrum of light we collect from it is a transmission from a time we can scarcely imagine, a time when galaxies were just assembling and matter was only beginning to settle into the familiar structures we recognize today. And the significance of that light lies in what it contains. Within the spectral fingerprint of Methuselah lies information about the physical conditions of the universe long before Earth had oceans, before dinosaurs walked, before atoms here ever formed complex chains of life. This star, designated HD 140283, appears almost modest through telescopes compared to the brighter, flashier stars that populate our night sky. And yet, its very dimness is part of its ancient character. The reason it doesn't shine with the intensity of our sun or the blazing brilliance of young blue giants is not because it lacks energy, but because its structure has aged in a finely balanced way. Its core fusion processes are more restrained, its envelope more expanded and cool. Methuselah has long passed the main sequence phase of its life. It has evolved into a subgiant, a stage where hydrogen fusion in the core ceases and begins instead in a shell around the core, causing the star to expand slightly and grow cooler on the surface. This subgiant status offers astronomers an incredibly useful trait. It places Methuselah in a narrow, well-understood phase of stellar evolution that makes it easier to model accurately. For younger stars, which can be burning hydrogen in various ways or exist in turbulent, rapidly changing phases, modeling exact ages is much more difficult. But with Methuselah, its slow, methodical transition gives scientists a rare chance to pin down an age that can be tested against cosmological models. And that's where the intrigue deepens. For years, scientists placed the age of HD 140283 at about 14.5 billion years, give or take 0.8 billion. That's potentially older than the universe's currently accepted age of 13.8 billion years as derived from the cosmic microwave background radiation and expansion rate data provided by instruments like the Planck satellite. How can something inside the universe be older than the universe itself? This discrepancy is not ignored. It has sparked serious scientific debate and re-evaluation of both stellar and cosmological models. There are several possible explanations for the age gap. Some involve adjustments to the models of stellar evolution, suggesting that uncertainties in opacity, convective behavior, or helium content might skew the age calculation. Others involve the cosmological parameters used to calculate the universe's age, like the Hubble constant, which defines how fast the universe is expanding. The Hubble constant itself is a source of ongoing tension in astrophysics. Different methods of measuring it produce different results. Observations of the early universe using the cosmic microwave background suggest one value, while measurements using supernovae and Cepheid variables in the local universe suggest a higher one. This disagreement, known as the Hubble tension, has led some physicists to suggest new physics may be needed, perhaps modifications to dark energy models, or even the existence of unknown particles that affect the universe's expansion rate. If our cosmic clock is off, then perhaps Methuselah isn't older than the universe. Perhaps our understanding of time itself is incomplete. But even if the discrepancy is resolved in favor of a younger Methuselah, the star remains an extraordinary case. Its estimated age still places it as one of the oldest known stars in existence. It is a primordial survivor from a time so distant that no star we can see has ever bridged so much history. It predates the Milky Way's spiral arms. It predates most of the stars we can see with the naked eye. In a way, it is like finding a living dinosaur, or something even older, wandering a modern landscape, unchanged, untouched, enduring. Methuselah's existence also brings forward a greater awareness of stellar population types. In the field of astrophysics, stars are often classified into three populations based on their metallicity, which is the amount of elements heavier than helium found within them. Population 1 stars, like our Sun, are rich in metals. They formed in a chemically evolved galaxy and have relatively short lifespans. Population 2 stars, like Methuselah, are metal poor, older, and generally found in the galaxy's halo or globular clusters. Then there's the most elusive group, Population 3 stars. These were the very first stars in the universe, composed almost entirely of hydrogen and helium, and no direct evidence of them has yet been found. Methuselah, while not a Population 3 star, is about as close as we've come to finding a direct descendant of that first generation. It was likely born just after the population 3 stars seeded the universe with the first heavier elements via supernova explosions. Its low metallicity confirms this origin. In fact, its elemental composition tells a subtle but powerful story, a universe in transition, from pure primordial gases to a cosmos just beginning the long alchemical process of forging heavier elements, the foundation of all planets, moons, and eventually life. The science of stellar spectroscopy allows us to determine the relative amounts of elements like iron, carbon, oxygen, and more in Methuselah. These elements are like a chemical diary, each one a marker of the processes that occurred before the star formed. Iron, for example, is generally produced in supernovae. The fact that Methuselah contains only trace amounts suggests that it formed shortly after the first supernovae went off in the early universe. In contrast, stars like the Sun are loaded with iron and other metals, showing that they were born in a universe that had already undergone multiple generations of star formation and death. This elemental scarcity is not just a curiosity, it also affects the way Methuselah formed and evolved. Low metallicity stars are less opaque, allowing energy to escape more easily from their cores. This in turn influences the rate of fusion and the size of the star. These differences must all be accounted for when calculating a star's age and modeling its future. In Methuselah's case, its low opacity means its energy budget has been managed extremely efficiently. This helps explain why it has lived for so long, and why it appears so stable and enduring. Methuselah's longevity invites us to think beyond the human timescale. It forces us to acknowledge that time in the universe flows on a scale far beyond what we can truly comprehend. 1 billion years is an unimaginable stretch for our brief lifespans, and yet Methuselah has lived 14 of those. For most of its existence, Earth was not even a whisper in the cosmic imagination. And now here we are, tiny creatures looking up at a star so old it breaks our theories, measuring it, studying it, trying to grasp its message across the chasm of time. It's also worth noting that Methuselah isn't alone in this ancient lineage. There are other stars with similar properties, ultra-metal-poor stars, found throughout the halo of the Milky Way and in neighboring dwarf galaxies. Some of these may also challenge our assumptions about the early universe. One such star, SMSS J03130.36-670839.3, found in the galactic halo, is nearly devoid of iron, suggesting it formed directly from the gas left behind by a population 3 star. While it may not be older than Methuselah, it represents a similar era in cosmic history, a time when stars were just beginning to shape the universe we now inhabit. Methuselah, therefore, serves not just as a case study, but as an anchor. An anchor in time, an anchor in knowledge, an anchor in mystery. It connects us to the very beginning while existing in our present. Its light, its age, its orbit, and its chemical fingerprint are all threads in the great tapestry of cosmic evolution. And the more we pull on those threads, the more we uncover about where we come from, and perhaps, where we're going. As we continue to explore the mysteries surrounding Methuselah, the implications stretch far beyond the star itself. The presence of this ancient cosmic relic in our galaxy brings into question our entire understanding of stellar life cycles, the formation of galaxies, and even the broader narrative of cosmic evolution. Its unusual age relative to the age of the universe reveals something important. There is still so much we don't fully understand about the processes that govern the birth, life, and death of stars. In astronomical terms, a star's age is calculated through a combination of observational data and theoretical models. These models include a variety of factors, from a star's chemical composition, metallicity, temperature, luminosity, and mass to its evolutionary phase. For most stars, this process is relatively straightforward. However, stars like Methuselah, which appear to have formed in the early universe with almost no metals and have lived far longer than expected, defy the standard expectations. For decades, the understanding of stellar evolution has been based on the assumption that once a star runs out of hydrogen in its core, it will move on to the next phase of its life, ultimately exhausting its nuclear fuel and undergoing significant expansion into a red giant or supergiant. Stars like Methuselah, however, present a challenge to that conventional understanding. This raises important questions about what happens in the lives of stars that are born in different, more primordial environments. It's also worth noting that the exact process of how stars like Methuselah formed has a direct impact on our understanding of the early universe. In a universe that was once primarily composed of hydrogen and helium, stars like Methuselah were among the first to forge the heavier elements through nucleosynthesis. The first generation of stars, often referred to as population 3 stars, were composed almost entirely of hydrogen and helium, the two lightest elements. When these stars went supernova, they released heavier elements like carbon, oxygen, and iron into space, enriching the interstellar medium. These elements were then used to form new generations of stars, including stars like Methuselah, which bear the signatures of those first supernovae. By studying the chemical composition of stars like Methuselah, astronomers can trace the story of this primordial nucleosynthesis and better understand how the early universe transformed from a featureless expanse of hydrogen and helium into the complex, multi-element environment that would give rise to planets, life, and everything we know today. The importance of these ancient stars extends to the search for the first galaxies. If stars like Methuselah formed early in the universe's history, then they could have existed alongside some of the first galaxies, which also formed from the primordial gas. By studying these ancient objects, astronomers hope to piece together a clearer picture of how galaxies, and even our own Milky Way, evolved over billions of years. The stars in the Milky Way's halo, where Methuselah resides, are believed to be relics of the galaxy's formation, formed from gas that was initially expelled during the collapse of the first galaxies. The study of these stars offers a direct window into the past, enabling astronomers to better understand the Milky Way's early history. In addition to its role in stellar evolution, Methuselah also highlights another fascinating aspect of modern astronomy: the precision of modern measurement techniques. The exact measurement of Methuselah's age, compared to the age of the universe, was made possible by advancements in technology, particularly in the field of astrophysical modeling and the use of large telescopes. Instruments like the Hubble Space Telescope and ground-based observatories allow astronomers to measure the star's brightness, temperature, and spectral lines with extraordinary precision, providing data that can be used to refine the star's age. However, even as these measurements improve, they still carry a level of uncertainty, particularly when it comes to the calculation of a star's age. The main source of uncertainty lies in the assumptions made during the modeling process. These models are based on our current understanding of stellar physics, which itself is an evolving field. For example, the precise behavior of stellar convection, the motion of material within a star's outer layers, can have a significant impact on a star's evolution, yet it is still not fully understood. Similarly, the treatment of chemical mixing within a star's interior remains an area of ongoing research. The idea that a star could potentially outlive the very universe it is part of is an enthralling paradox that fuels debates in the scientific community. But rather than suggesting a flaw in our cosmological models, it emphasizes how little we still know about the complexities of the universe. Each mystery, each new discovery, is a step forward in a journey of understanding that continues to stretch the boundaries of human knowledge. It is a journey that makes discoveries like Methuselah's age not just fascinating in their own right, but important pieces of a larger puzzle that scientists, philosophers, and dreamers alike are eager to solve. The broader implications of Methuselah's story are also interwoven with the concept of cosmic inflation, the theory that the universe expanded at an incredibly rapid rate just moments after the Big Bang. Some cosmologists have proposed that the unexpected age of Methuselah could be a clue that certain models of cosmic inflation need to be adjusted. The universe's inflationary period might have been more complex than originally thought, with variations in the rate of expansion across different regions of space. These subtle variations could explain why certain stars like Methuselah appear older than expected, suggesting that our models of the early universe may need to account for more than just a uniform, isotropic expansion. This brings us back to a central point. The mystery of Methuselah's age is not just a scientific curiosity. It is a fundamental challenge to how we perceive time, space, and the universe itself. Time, as we experience it, is a human concept, one that relies on the cyclical nature of the Earth's rotation and orbit around the Sun. The cosmic clock, however, operates on a far grander scale, one that challenges the very foundation of our understanding of history. Methuselah's ancient light carries with it echoes of events long past, and those echoes resonate through the vastness of space, reminding us that the universe is far older, far more complex, and far more mysterious than we can possibly comprehend. But what can we learn from all of this? The story of Methuselah is ultimately a reminder that science is an ongoing endeavor. Every answer leads to more questions, and every discovery builds upon the foundations of what came before. Methuselah's age, along with the questions it raises, is an invitation to explore the deepest corners of the cosmos. It challenges us to reconsider the assumptions that shape our view of the universe, urging us to refine our models, expand our horizons, and ultimately embrace the mystery of existence. As we look to the stars, we are confronted not only with the unimaginable scale of the universe but also with the humbling realization that we are just beginning to understand the depths of time and space. The story of Methuselah is not just a tale of one ancient star, it is a metaphor for our own search for knowledge. And just as Methuselah continues to burn through the eons, so too does humanity's quest for truth persist, burning brightly in the vast, dark expanse of the cosmos. As we continue, the story of Methuselah serves as a perfect example of the mysteries we continue to unravel about the universe. It's more than just the anomaly of an ancient star, it's a reminder that the cosmos is still full of secrets waiting to be discovered. Methuselah's age is not just an outlier in terms of stellar lifespans. It's a symbol of how our understanding of the universe is constantly evolving. The more we learn, the more we realize how much we don't yet know, especially about the early universe, the formation of stars, and the fundamental laws of physics that govern cosmic structures. The cosmic landscape Methuselah resides in, the halo of the Milky Way galaxy, is itself an area rich with relics from the early universe. Stars in this region, many of which are quite old, provide a glimpse into the conditions that existed when the universe was just a fraction of its current age. These ancient stars hold within them the history of the first generations of stars and galaxies that populated the universe after the Big Bang. By studying stars like Methuselah, we get closer to understanding the birth of galaxies and the processes that led to the formation of the Milky Way itself. However, Methuselah's very existence raises another profound question. If it's older than the universe as we currently understand it, does that suggest that the conventional Big Bang model might be flawed? The age paradox isn't easily explained away by simple miscalculations or errors in measurement. It's a deeply troubling anomaly that forces scientists to reconsider aspects of their foundational models. Could it be possible that our current cosmological theories, which place the age of the universe at around 13.8 billion years, need to be revised? If the universe is truly older than that, what does this mean for our understanding of cosmic inflation, the expansion of the universe, and the precise mechanisms that led to the formation of the stars and galaxies we see today? The introduction of such paradoxes challenges us to think about time itself in new ways. Traditionally, time has been understood as linear, with a clear origin in the Big Bang. But with phenomena like Methuselah pushing the boundaries of our comprehension, we're forced to consider the possibility that time might not be as straightforward as it appears. Could the universe have experienced phases of existence beyond the known Big Bang? Could there be regions of space and time that operate on different scales, allowing for stars like Methuselah to form in ways that defy conventional understanding? One of the most exciting implications of Methuselah's age is that it offers a unique opportunity to test the fundamental laws of physics. If we take Methuselah as an outlier, then we must ask whether there are other stars out there with similar anomalies. Are there more ancient stars hidden within the farthest reaches of our galaxy or beyond, waiting to be discovered? And if we find them, what will they tell us about the underlying principles of the universe? Methuselah's age forces us to ask whether the fundamental constants we rely on in our models of stellar evolution, such as the rates of nuclear fusion, the physics of convection, and the behavior of matter under extreme conditions, are truly constant across time and space. If they are not, then our understanding of the cosmos must undergo a profound shift. Moreover, the discovery of Methuselah prompts us to ask questions not just about stars, but about the broader structure of the universe. What is the fate of these ancient objects, And how do they fit into the larger evolutionary picture of the universe? While most stars, after billions of years, will end their lives in spectacular supernova explosions, the future of stars like Methuselah remains uncertain. With its extremely low metallicity, the star might not have gone through the same evolutionary process as younger stars, which could mean it will eventually end its life in an entirely different way. Could it be possible that Methuselah will simply burn out quietly, becoming a white dwarf, or will it eventually explode in a way that has yet to be fully understood? Another fascinating aspect of Methuselah is its place in the broader context of stellar populations. Stars are generally classified into populations based on their age and chemical composition. Population 1 stars, which are relatively young and rich in metals, are found in the spiral arms of galaxies like the Milky Way. Population 2 stars, like Methuselah, are older, have lower metallicity, and are typically found in the galactic halo or in globular clusters. These stars are relics from the early universe, providing a snapshot of the conditions that existed billions of years ago. What makes Methuselah particularly intriguing, however, is the fact that it seems to defy the expectations for stars of its class. By examining stars like Methuselah, astronomers hope to gain insight into how the universe's first stars formed and how the early elements, hydrogen and helium, were transformed into the elements that make up the world around us. The further we venture into understanding Methuselah, the more we come to appreciate how much we've yet to learn. As scientists continue to probe the secrets of the cosmos, stars like Methuselah remind us of the limits of human understanding. With every new discovery, we encounter a universe that is more mysterious and complex than we ever imagined. Methuselah itself, a star older than the universe according to current models, is a paradox wrapped in a riddle, one that may eventually lead to a revolution in our understanding of space, time, and the very fabric of the cosmos. The study of Methuselah's age might also hold the key to understanding the nature of cosmic expansion. While we traditionally think of the Big Bang as the starting point for both space and time, the anomaly of Methuselah's age forces us to rethink this. Could the universe have undergone a more complex, multi-phase process of expansion that is not reflected in our current models? Could there be remnants of an earlier phase of the universe, preserved in ancient stars like Methuselah, that challenge the idea of a singular, uniform beginning? These are the kinds of questions that inspire the most groundbreaking research in modern astrophysics. Additionally, the existence of Methuselah invites us to consider how stars like it might continue to contribute to the universe's evolving structure. While stars like Methuselah are incredibly rare, they offer insight into the very foundations of stellar formation. The study of such stars can help us understand how the first galaxies and structures in the universe took shape. Stars like Methuselah, with their incredibly low metallicity, provide an important clue to understanding the conditions under which the first galaxies, stars, and planets formed. As we look forward, the story of Methuselah will continue to evolve, providing astronomers and physicists with new insights and challenges. It's a reminder that the universe is full of surprises, and even our most fundamental assumptions may not be as secure as we think. What we know about stars, galaxies, and the universe as a whole is constantly in flux, and discoveries like Methuselah's age are just the beginning of a much deeper journey into the heart of cosmic mysteries. Methuselah may be more than just the oldest star we know of. It might represent a turning point in how we view the universe itself. With every new discovery, the boundaries of our understanding are pushed, and Methuselah is a prime example of how the universe continues to challenge our most deeply held beliefs. As we continue to probe the mystery of Methuselah, we begin to appreciate the many layers of complexity that surround it. The star is not just a relic from the early days of the universe. It is a cosmic beacon that illuminates the gaps in our understanding of stellar evolution, the formation of galaxies, and the age of the cosmos itself. Methuselah's anomalous age forces us to confront one of the fundamental questions in astrophysics. What if the current models of stellar and cosmic evolution are incomplete, or even wrong? The more we examine Methuselah, the more it pushes the boundaries of conventional science and compels us to reconsider the very framework in which we understand the universe. As astronomers continue to study Methuselah and other ancient stars, they are constantly faced with the limitations of our current observational technology. While we've come a long way in our ability to detect and study distant stars, there are still many uncertainties in the process of measuring their age, composition, and behavior. The age of a star like Methuselah is determined through a variety of methods, each of which carries its own uncertainties. For example, astronomers often use models of stellar evolution to estimate a star's age, but these models are based on certain assumptions about how stars of different compositions and masses behave. If any of these assumptions are incorrect, the age estimate for a star could be off by millions or even billions of years. Another challenge lies in the measurement of the star's chemical composition. Stars like Methuselah are considered population II stars, meaning they are composed primarily of hydrogen and helium, with only trace amounts of heavier elements. These stars are often located in the galactic halo, far from the more active regions where new stars are constantly forming. The low metallicity of stars like Methuselah makes them difficult to study in detail. While we can measure their light and determine some of their properties, understanding their true composition requires highly precise measurements of their spectra, a process that is still limited by the sensitivity of our instruments. Yet, despite these challenges, the study of ancient stars like Methuselah has the potential to reveal new insights into the early universe. For example, by understanding the chemical makeup of these stars, scientists can learn more about the primordial materials that existed before the first stars and galaxies formed. This could help us answer fundamental questions about the nature of the universe's earliest moments. What were the conditions like in the aftermath of the Big Bang? How did the first stars form, and how did they contribute to the creation of the elements that we see in today's stars and planets? The study of stars like Methuselah also raises fascinating questions about the future of stellar evolution. As stars age, they go through various stages of their life cycle, from their initial formation to their eventual demise. Most stars, including our own Sun, will eventually become red giants and then end their lives as white dwarfs. However, stars like Methuselah, with their extreme age and unique composition, might follow a different path. Some researchers speculate that such ancient stars could have unusual internal structures that could affect their behavior as they approach the end of their lives. What makes this particularly intriguing is the idea that stars like Methuselah might provide clues about how the universe's first generation of stars evolved and died. These first stars, known as population III stars, were likely massive, hot, and short-lived, burning through their fuel at an incredible rate. They would have released vast amounts of energy and heavy elements into the surrounding space, enriching the interstellar medium and paving the way for the formation of later generations of stars and planets. While no population III stars have yet been observed, stars like Methuselah may contain traces of the materials they left behind, giving us a glimpse into the processes that shaped the early universe. In addition to their role in the evolution of the cosmos, stars like Methuselah also provide important clues about the nature of time and space itself. As we continue to explore the farthest reaches of the universe, we encounter more and more examples of phenomena that challenge our understanding of the fundamental laws of physics. The age paradox presented by Methuselah is just one such example. The fact that this star seems to be older than the universe itself raises profound questions about the nature of time and space. Could time, as we understand it, be different in certain parts of the universe? Could there be regions of space where the laws of physics operate differently, allowing for the existence of objects like Methuselah? The existence of Methuselah also prompts us to reconsider the assumptions we've made about the structure and evolution of the universe. In the standard model of cosmology, the universe began with the Big Bang around 13.8 billion years ago, and has been expanding ever since. This model provides a framework for understanding the formation of galaxies, stars, and other cosmic structures. However, the discovery of a star that appears to be older than the universe suggests that there may be gaps in this framework. Could the universe have undergone a more complex, multi-phase evolution than we currently understand? Could there have been earlier periods of cosmic growth that we have yet to detect or comprehend? Methuselah's age paradox also raises intriguing possibilities about the nature of cosmic inflation. The theory of cosmic inflation suggests that the universe underwent a period of extremely rapid expansion in the moments after the Big Bang, stretching space-time to incredible distances in a fraction of a second. While this theory is supported by a variety of observations, the existence of a star older than the universe could imply that there may be aspects of inflation that we don't fully understand. If the universe expanded so rapidly in its early moments, could there be regions of space where time behaves differently, allowing for the existence of ancient stars like Methuselah? Another fascinating question that arises from the study of Methuselah is the role that dark matter and dark energy might play in the universe's structure and evolution. These mysterious substances, which make up most of the mass and energy in the universe, have yet to be directly observed, but their influence is felt in a variety of ways. Dark matter, for example, is thought to be responsible for the gravitational effects that keep galaxies from flying apart, while dark energy is believed to be driving the accelerated expansion of the universe. Could dark matter or dark energy play a role in the formation of stars like Methuselah, or in the peculiar properties that make them so unique? While we don't yet know the answer to these questions, the study of ancient stars like Methuselah could provide valuable clues about the elusive nature of dark matter and dark energy. The story of Methuselah is a story of discovery, mystery, and wonder. It is a reminder that the universe is far more complex than we can imagine, and that every new discovery brings us closer to understanding the profound truths that govern our existence. As scientists continue to investigate the nature of stars like Methuselah, they are not just uncovering the secrets of a distant star, they are unlocking the deepest mysteries of the universe itself. The questions raised by Methuselah, from its age paradox to its role in the evolution of galaxies, are not just challenges for astronomers and physicists. They are invitations for all of us to explore the cosmos with a sense of awe and curiosity. As our understanding of the universe continues to evolve, so too will our understanding of stars like Methuselah. The age of this ancient star may continue to be a source of fascination for years to come, but it is also a testament to the ever-expanding boundaries of human knowledge. Just as Methuselah stands as a relic of the early universe, it also serves as a beacon for the future, reminding us that there is always more to discover, and that the universe will continue to surprise us in ways we can't yet imagine. As the study of Methuselah progresses, researchers are constantly refining their techniques and expanding their methods to uncover more secrets about the star's true nature. In the realm of stellar astronomy, Methuselah is not just an anomaly, it is a challenge, a puzzle that requires an evolving understanding of the laws of physics. To truly comprehend the star's enigmatic age and characteristics, astronomers and astrophysicists must dive deep into the interplay of light, gravity, and time itself. One of the most pivotal tools used in the study of stars like Methuselah is the spectrometer. A spectrometer allows scientists to analyze the light emitted by distant stars, breaking it down into its constituent wavelengths. This enables them to determine the chemical composition, temperature, and velocity of the star. The spectrum of a star, or its fingerprint, tells scientists everything they need to know about the elements present, the star's surface temperature, and its motion through space. For Methuselah, scientists have used this tool to deduce its high metal deficiency, which is a key characteristic of ancient stars. The lower the concentration of heavy elements like iron and calcium, the older the star is likely to be. This, in part, is why Methuselah's discovery became so remarkable. If the star's age is accurately estimated, it would imply a surprising mismatch between the universe's known age and the age of its oldest star. Methuselah's age has also prompted a re-examination of the processes involved in stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones, creating the elements that form the building blocks of everything from planets to people. In the early universe, stars formed from the primordial hydrogen and helium left behind by the Big Bang. These first stars, known as population 3 stars, are believed to have been much larger and hotter than modern stars, burning out quickly and leaving behind massive remnants of their stellar cores. While no direct observation of population 3 stars has yet been made, Methuselah provides indirect evidence of their existence. The low metal content of Methuselah, coupled with its extreme age, suggests that it may have formed in the early stages of the universe, potentially from the very materials produced by these ancient behemoths. The study of Methuselah also offers valuable insights into the life cycle of stars. As a population 2 star, Methuselah is in a later stage of its evolution compared to younger stars like our Sun. Stars like Methuselah are typically in the horizontal branch phase of their life cycle. In this phase, stars burn helium in their cores, which gives them a distinctive spectrum and color. These stars are nearing the end of their stable fusion process and are in the process of slowly transitioning into the red giant phase. The fact that Methuselah is still shining so brightly, despite its extreme age, suggests that the star's core is in a delicate balance between its gravitational pull and the pressure exerted by the fusion of helium and other elements. This balance, which is a crucial part of stellar evolution, may hold the key to understanding how such ancient stars are able to endure for billions of years. Furthermore, Methuselah's age paradox raises the intriguing possibility that stars like it could play a role in the larger cosmological framework of dark matter and dark energy. Dark matter, which accounts for about 27% of the universe's mass, is thought to be an invisible form of matter that exerts gravitational influence but does not interact with light in the same way that ordinary matter does. Dark energy, on the other hand, is a mysterious force believed to be driving the accelerated expansion of the universe. While the exact nature of both dark matter and dark energy remains elusive, stars like Methuselah could provide valuable clues about how these phenomena fit into the overall structure of the universe. One of the most tantalizing possibilities is the idea that Methuselah's peculiar characteristics may be a direct result of its interaction with dark matter. Some theories suggest that the presence of dark matter could alter the way stars evolve, potentially allowing for longer lifespans or different stellar properties. If this theory is correct, it could change the way we think about the entire life cycle of stars. Understanding how dark matter interacts with stars like Methuselah could lead to a more unified theory of astrophysics, one that incorporates both visible matter and the mysterious dark substances that dominate the cosmos. The ongoing research into Methuselah has also sparked new interest in the search for other ancient stars throughout the universe. Astronomers are now using more advanced telescopes and observatories, such as the Hubble Space Telescope, to look deeper into space and identify other potential candidates that could be even older than Methuselah. These stars, if discovered, could provide further insight into the processes of cosmic evolution, the formation of galaxies, and the origins of the universe itself. The discovery of other stars that challenge our understanding of stellar lifespans and cosmic time scales could potentially alter the course of astrophysics and cosmology in profound ways. As more data is gathered from distant galaxies, scientists hope to uncover even more details about the conditions under which ancient stars like Methuselah were born. Did they form in the same way as stars do today, or was their creation a result of different processes, driven by the unique conditions of the early universe? What role did cosmic inflation play in their formation, and how did the first stars set the stage for the birth of galaxies, planets, and even life itself? Another exciting possibility is the role that these ancient stars play in the broader context of galaxy formation. The early universe was a chaotic place, filled with the remnants of the Big Bang and a rapidly expanding field of matter. Galaxies began to form as clumps of gas and dust began to collapse under the influence of gravity, leading to the creation of the first stars and stellar systems. The study of ancient stars like Methuselah can offer a glimpse into this process, helping astronomers understand how the first galaxies formed and how the large-scale structure of the universe began to take shape. The birth of stars and galaxies is intricately tied to the presence of black holes. As massive stars like Methuselah reach the end of their lives, they begin to collapse under their own gravity, potentially forming a black hole. Black holes are among the most mysterious and fascinating objects in the universe, and their study has led to groundbreaking discoveries in our understanding of space-time, gravity, and the fabric of the cosmos. While Methuselah is not likely to collapse into a black hole, the processes that drive the formation of black holes are closely tied to the life cycles of stars. By studying stars like Methuselah, we can gain a better understanding of how black holes form, how they evolve, and what role they play in the grand narrative of the universe's development. The ongoing research into Methuselah and other ancient stars is just one piece of the puzzle in our quest to understand the universe. With each new discovery, we inch closer to unraveling the mysteries of cosmic time, stellar evolution, and the nature of the universe itself. The study of stars like Methuselah reminds us that the universe is far older and more complex than we could ever have imagined. While we may never fully comprehend the true nature of the cosmos, our exploration of these ancient relics of the universe brings us one step closer to understanding our place in the grand expanse of time and space. Through the lens of Methuselah, we see that there are still countless mysteries waiting to be uncovered in the vast expanse of the cosmos. As new technologies and methods of observation continue to develop, our understanding of the universe will only grow deeper and more nuanced. What we know today is just a fraction of what lies beyond our reach, and the mysteries of stars like Methuselah will continue to challenge our imagination and drive us to explore the unknown. The allure of ancient stars and their secrets will continue to captivate the minds of scientists, philosophers, and stargazers for generations to come. As we peer into the heavens and look back in time, we are reminded that the universe is not just a collection of stars, planets, and galaxies. It is a vast, intricate tapestry of stories, each one waiting to be uncovered. And at the heart of it all lies the quest for knowledge, a journey that will take us to the farthest corners of the universe and into the deepest recesses of time itself. The allure of stars like Methuselah is not only in their age but in the questions they raise about the very nature of the universe. When we observe such ancient and mysterious objects, we are not just looking at distant celestial bodies, but at windows into the past, a past that predates the formation of our solar system, our planet, and even the Earth itself. As we look further back into the universe's timeline, we begin to understand more about the processes that form not only stars but the very elements that make up everything around us. The process of stellar evolution, which includes the birth, life, and death of stars, is one of the key themes that comes into play when studying stars like Methuselah. While we tend to think of stars as eternal, or at least long-lived entities, their lives are relatively brief on cosmic timescales. The birth of a star occurs when vast clouds of gas and dust collapse under their own gravity. In the case of Methuselah, its journey began billions of years ago, at a time when the universe was still in its early stages. This star was likely formed from the remnants of older stars or from material that had been floating in space for a long time, perhaps even since the universe's inception. Understanding how stars like Methuselah evolve is key to understanding their significance in the universe. Like all stars, Methuselah has gone through several stages of its life, from its initial formation to its current status as a relatively stable, middle-aged star. But unlike younger stars, Methuselah's age means it has passed through a variety of different phases, some of which we can only study through the lens of modern astrophysics. What makes stars like Methuselah particularly fascinating is that their lives are intertwined with the larger cosmic processes that shape galaxies and even the structure of the universe itself. Ancient stars like Methuselah are key players in the formation of galaxies, influencing how matter is distributed and how galaxies evolve. The fact that Methuselah has endured for so long suggests that it is a survivor of the earliest phases of stellar formation, making it a relic from a time before galaxies as we know them existed. Stars like Methuselah hold clues about the conditions of the early universe, the forces at work, and the ways in which galaxies formed. One critical piece of the puzzle that Methuselah helps to reveal is the process of stellar nucleosynthesis, the mechanism by which stars produce the heavy elements necessary for the formation of planets and life. The elements that make up the Earth, including carbon, oxygen, nitrogen, and iron, were all forged in the hearts of stars over billions of years. When stars like Methuselah reach the end of their lives, they explode in violent supernovae, releasing these elements into the surrounding space. This process of enrichment is essential for the formation of new stars, planets, and even life itself. In studying stars like Methuselah, we gain insight into the origins of these elements. Methuselah, with its low metallicity, is thought to be one of the earliest survivors of this stellar enrichment process. The lack of heavy elements in its composition tells us that it was likely formed at a time when the universe had not yet been sufficiently enriched by previous generations of stars. This, in turn, suggests that stars like Methuselah are some of the oldest stars in existence, stars that formed in the early stages of the universe and have managed to survive through the ages. However, the low metallicity of stars like Methuselah is not just a clue about their age. It is also a reflection of the conditions of the early universe. In the first few billion years after the Big Bang, the universe was composed primarily of hydrogen and helium, with only trace amounts of heavier elements. Stars like Methuselah, which formed from this primordial gas, are effectively time capsules, preserving a snapshot of the universe's early composition. This provides valuable information about how stars and galaxies formed and evolved during the earliest stages of the universe. The study of stars like Methuselah is also helping us to understand the process of cosmic inflation. Cosmic inflation is a theory that suggests that the universe underwent a rapid expansion in the first few moments after the Big Bang, leading to the large-scale structure of the universe we see today. The properties of ancient stars like Methuselah could provide valuable insights into how inflationary processes affected the formation of galaxies and stars. Understanding these processes could help us better understand the large-scale structure of the universe, from the distribution of galaxies to the formation of massive black holes at the centers of galaxies. Furthermore, the study of such ancient stars has far-reaching implications for cosmology, the study of the universe's origin, evolution, and eventual fate. Methuselah, as one of the oldest known stars, provides a unique glimpse into the early universe, a time when the first galaxies were forming, and the universe was still in its infancy. By studying stars like Methuselah, scientists hope to unlock the secrets of the universe's origins and gain a deeper understanding of the fundamental forces that have shaped the cosmos. In particular, scientists are interested in how the very first stars, known as population 3 stars, contributed to the formation of the first galaxies. These stars were made almost entirely of hydrogen and helium, and their explosive deaths created the first heavy elements, seeding the universe with the building blocks for future star and planet formation. As our technology improves, we are able to peer further back into the universe's history. New telescopes and observatories, such as the James Webb Space Telescope, JWST, are poised to revolutionize our understanding of stars like Methuselah. The JWST, with its advanced infrared capabilities, will allow astronomers to look at some of the oldest and most distant objects in the universe. This will help us gain a better understanding of how stars like Methuselah fit into the broader picture of cosmic evolution. One of the most profound mysteries that stars like Methuselah present is the nature of dark matter. Dark matter is one of the biggest unsolved mysteries in astrophysics. It is thought to make up about 27% of the universe's mass, but it does not interact with light in the same way as ordinary matter, making it difficult to detect. The role of dark matter in the formation and evolution of stars is still not well understood. Some theories suggest that dark matter could influence how stars form and evolve, potentially affecting their lifespans and properties. Stars like Methuselah may hold the key to understanding how dark matter interacts with normal matter, offering a unique opportunity to explore the complex relationship between the visible and invisible parts of the universe. Methuselah's enigmatic properties are a reminder that the universe is full of surprises. The more we learn about stars like Methuselah, the more we realize how little we truly understand about the cosmos. As we continue to explore the farthest reaches of space, we will undoubtedly encounter more objects that challenge our current understanding of astrophysics and cosmology. These discoveries will inspire new theories, new technologies, and new ways of thinking about the universe. The search for ancient stars like Methuselah is not just a quest for knowledge about the past, it is a quest to understand the future. By studying the oldest stars in the universe, we gain a better understanding of the processes that will shape the future of the universe. Stars like Methuselah offer a glimpse into the eventual fate of our own sun and the stars that will follow. Understanding the life cycle of stars, from their formation to their ultimate death, is crucial for understanding the long-term evolution of the universe. As we continue to study stars like Methuselah, we are reminded that the universe is a vast and mysterious place, full of surprises and wonders that challenge our imagination. The journey of discovery is far from over, and the secrets that lie ahead will continue to captivate and inspire future generations of scientists, astronomers, and curious minds alike. As we venture deeper into the cosmos, studying stars like Methuselah, it becomes clear that we are not merely exploring distant points of light, we are peering into the very fabric of time itself. The farther we look into the universe, the further back we are essentially looking at the history of everything, the birth of stars, the formation of galaxies, and the first moments of the universe after the Big Bang. The study of stars like Methuselah, which challenge our understanding of the universe's age, only deepens the mystery of the cosmos and sparks questions that we have yet to answer. One of the most profound aspects of studying such ancient stars is the role they play in helping us understand the cosmic timeline. The age of Methuselah, estimated to be over 13.7 billion years old, provides a window into a universe that is still in its infancy compared to the current age of 13.8 billion years. The question arises, how is it possible for a star to exist that predates the universe's age estimate? This anomaly has led scientists to re-examine their assumptions about the early universe and the methods used to calculate the age of stars and the universe itself. Stars like Methuselah, which are older than previously expected, force us to reconsider how we measure cosmic time. The discrepancy between the estimated age of the star and the universe's age is significant, and it has prompted astronomers to think more critically about the techniques they use to calculate the age of stars. Traditionally, astronomers estimate the age of a star by looking at its chemical composition and its place in the Hertzsprung-Russell diagram, which is a graph that plots stars based on their luminosity and temperature. However, Methuselah's apparent age challenge suggests that this method might not be as foolproof as once thought. The star's age discrepancy could be related to its chemical composition, particularly its low metallicity. Metallicity is the amount of elements heavier than hydrogen and helium found in a star. Stars like Methuselah, which have low metallicity, are thought to have formed at a time when the universe was still relatively poor in heavy elements, following the Big Bang's hydrogen and helium-rich composition. These stars represent a sort of primeval era in stellar evolution, one that is distinct from the stars that have formed more recently. Despite the initial surprise over the age of Methuselah, the star is still considered an important part of the cosmic puzzle. Its anomaly has driven further investigations into the nature of stellar age calculations. Perhaps it points to flaws in our current models of stellar evolution, or maybe it suggests that there are other factors at play that have not yet been accounted for. The challenge posed by stars like Methuselah serves as a reminder that science is always evolving, and what we think we know today might be completely reshaped by new discoveries tomorrow. The mystery of Methuselah's age also encourages a broader inquiry into the way that cosmic events, such as the formation of stars and galaxies, are understood in the context of universal time. How do we define the beginning of the universe, and how do we tie that to the age of individual stars? Understanding the time frame of stellar evolution is not just about understanding the life cycle of stars. It's about understanding the broader cosmic narrative. Stars like Methuselah are pivotal to this narrative, as they help us map out the structure and history of the universe in ways that are still being uncovered. As we continue to study the star, scientists are looking at multiple angles of investigation to explain its apparent age discrepancy. One of the most promising avenues of research is the potential discovery of new physics that could alter our understanding of stellar aging. For instance, the presence of exotic particles, changes in the way that stars burn their fuel, or the influence of dark energy and dark matter could potentially impact how stars evolve. If new models emerge that can reconcile the age of Methuselah with the age of the universe, this could mark a groundbreaking moment in astrophysics, offering new insights into the fundamental workings of stars and the universe. The discoveries that arise from studying stars like Methuselah are not limited to the realm of theoretical physics or astrophysics. The implications for other areas of science are just as profound. For instance, the formation of heavy elements in the cores of ancient stars like Methuselah provides insight into the processes that lead to the formation of planets and, ultimately, life. Understanding the processes by which the universe became enriched with elements like carbon, oxygen, and nitrogen, the building blocks of life, offers important clues for researchers studying the origins of life itself. The study of ancient stars also challenges the narrative that stars are simply isolated objects in space. In reality, they are part of an interconnected, dynamic system that stretches across vast distances. Each star, including Methuselah, plays a role in shaping its environment, from the formation of planets to the evolution of galaxies. Stars like Methuselah, which existed long before our solar system, provide a snapshot of what the early universe looked like, how the first generations of stars impacted the gas and dust surrounding them, eventually leading to the formation of galaxies and star clusters. Stars are not simply creators of elements and structures, but also custodians of the cosmic memory. By studying stars like Methuselah, we gain insight into the fundamental building blocks of the universe. These stars preserve the information about the early universe, helping us piece together the conditions that led to the formation of our solar system, our planet, and our own existence. The life cycle of a star is like a cosmic clock, marking the passage of time from the birth of the universe to the present moment. The mystery of Methuselah also highlights the importance of technological advancements in space observation. As our telescopes and observation methods become more advanced, we are able to peer deeper into the universe than ever before. The Hubble Space Telescope, for instance, has allowed astronomers to observe distant stars, galaxies, and nebulae, offering new insights into the universe's history. The upcoming James Webb Space Telescope promises to take this exploration to even greater heights, allowing scientists to observe the very first galaxies and stars that formed after the Big Bang. These advances in technology will be crucial for understanding stars like Methuselah. By observing these ancient celestial bodies with greater precision, we can learn more about their chemical composition, their temperature, and their age. We can also study their behavior in more detail, gaining insights into their internal processes, such as the way they generate energy and sustain themselves over billions of years. The more we learn about stars like Methuselah, the more we uncover about the universe's early history. The star also serves as a reminder of the inherent unpredictability of the cosmos. While scientists are constantly refining their models of stellar evolution, there are still aspects of the universe that defy explanation. The study of stars like Methuselah challenges our understanding of the fundamental laws of physics and reminds us that the universe is full of surprises. Each discovery we make raises new questions and new mysteries that beckon us further into the unknown. Methuselah is more than just an old star, it's a symbol of the ongoing journey of discovery that humanity is on in its quest to understand the universe. The anomalies surrounding its age are not roadblocks, but invitations to re-examine the assumptions that shape our understanding of the cosmos. As we continue to study Methuselah, we are not just uncovering the secrets of one particular star, but also opening the door to a deeper understanding of the universe itself. Each discovery made is a small step toward answering some of the most profound questions about the origins of everything, from stars and galaxies to the very atoms that make up our bodies. In a universe that spans billions of years and stretches beyond our comprehension, Methuselah stands as a reminder of how much we still have to learn. The journey of discovery is far from over, and the star will continue to captivate scientists and stargazers alike for years to come. It is a timeless beacon, inviting us to look deeper, think more profoundly, and wonder just how much more the universe has to teach us. As we continue to probe the mysteries surrounding Methuselah, the questions that arise go far beyond just the age of one star. They extend into the very foundation of our understanding of astrophysics, cosmology, and the timeline of the universe itself. Methuselah is not just an anomaly to be explained away. It is an opportunity to rethink the way we look at the cosmos, the stars that populate it, and the nature of time itself. Its existence challenges the established framework of our universe's birth, evolution, and ultimate fate, and it compels us to reassess our perceptions of what is possible in the realms of both science and philosophy. At the heart of the mystery of Methuselah lies a fundamental question: how did the universe evolve in the first few moments following the Big Bang? The traditional narrative suggests that after the initial expansion, the universe cooled, allowing matter to form and eventually leading to the creation of the first stars and galaxies. However, the discovery of stars like Methuselah raises questions about how early stars could have formed in such a manner as to defy what we thought was possible. The formation of such an old star requires a new model of stellar formation, one that accounts for the processes that might have led to the creation of stars older than the universe itself, something that could lead to dramatic shifts in our cosmological theories. Methuselah, as an ancient stellar relic, offers us a glimpse into a period of cosmic history that we have not been able to witness in other ways. Its formation likely occurred during a time when the universe was still in its infancy, and the cosmos was devoid of the heavy elements that came later from supernova explosions and the nucleosynthesis of elements in the cores of stars. The stars of this early period, sometimes referred to as population 3 stars, were primarily composed of hydrogen and helium. These stars were the first to ignite after the Big Bang and, over time, began to enrich the universe with the heavier elements necessary for the formation of planets, life, and everything we know today. What sets Methuselah apart from other stars in the Milky Way, and even from other population 2 stars, is its incredible age. The difficulty scientists face in reconciling Methuselah's age with that of the universe is not just an academic curiosity. It's a window into the way we must think about the very fabric of time. If Methuselah is indeed older than the universe's age estimate, what does that say about the methods we use to measure time and distance in space? Is the way we measure the universe's age in need of revision, or is it possible that our understanding of the physics governing stars and cosmic expansion needs a rethink? The traditional methods used to estimate the age of stars are based on the concept of stellar evolution, which takes into account a star's mass, temperature, and chemical composition. Over time, as stars like Methuselah age, they move through various stages of their life cycle, burning through their fuel and evolving into different types of stars. This process is governed by the laws of physics, but it also depends heavily on initial conditions, such as the star's metallicity. In Methuselah's case, its apparent age, which exceeds that of the universe, might be explained by unknown variables related to its formation or the peculiarities of its specific stellar evolution. Perhaps there is an aspect of the process we do not fully understand, or perhaps we have yet to factor in all the nuances of how early stars could have lived and died. These questions raise the possibility that the star's true age could be misunderstood due to limitations in current models of stellar physics. Perhaps there is a gap in our understanding of the behavior of stars in the early universe, leading to an underestimation of their lifespans. Alternatively, there might be an overlooked phenomenon, a force or interaction that could skew our calculations. We are left to wonder whether our fundamental concepts of time, space, and cosmic history are as reliable as we once thought. As we continue to study Methuselah, it also serves as a reminder that the universe is far more complex than we can currently comprehend. We may be on the cusp of a major breakthrough in our understanding of stellar evolution, cosmology, and the origins of the universe itself. Theories about the early universe, such as the idea that the Big Bang may not have been a singular event but part of an ongoing cycle of cosmic rebirth, could potentially offer new insights that make sense of anomalies like Methuselah. Beyond the scientific implications, Methuselah also invites philosophical musings about the nature of the cosmos. If there are stars that outlive the universe's age estimate, what does this say about the temporal nature of existence? The universe itself is constantly changing, with stars being born, dying, and evolving in a grand cosmic dance. But if a star like Methuselah can exist for such a length of time, what does this tell us about the nature of time in general? Is time an absolute force that flows forward in one direction, or is it something more fluid, more malleable than we currently understand? The existence of stars like Methuselah also raises important questions about the future of the universe. As stars age and die, they create the conditions for the next generation of stars to form. This cycle of birth and death is essential to the cosmic balance. But as we look at stars like Methuselah, we are also reminded that the universe has been evolving for billions of years, and it will continue to evolve long after we are gone. What does the future hold for stars like Methuselah? Will they eventually explode in a supernova, leaving behind remnants that could one day give birth to new celestial bodies? Or will they simply continue to fade into the background, their existence stretching on for unimaginable lengths of time? In a sense, stars like Methuselah embody the mystery and the beauty of the cosmos. They are the living remnants of a distant past, each one carrying with it a piece of the universe's history. The fact that such stars can exist, defying our expectations and challenging our understanding, only adds to the grandeur and complexity of the universe we inhabit. They remind us that there is still so much to discover, that there are still countless mysteries waiting to be unraveled, and that the cosmos is far from fully understood. Methuselah is more than just an old star, it's a symbol of the ongoing quest for knowledge. Its very existence invites us to look beyond the boundaries of our current understanding and to keep searching for answers, even when those answers seem elusive. As we look toward the future, the mysteries of the universe will continue to unfold, with stars like Methuselah guiding our way. And though we may never fully comprehend the true nature of these ancient celestial bodies, we can take solace in the fact that each discovery, no matter how small, brings us one step closer to understanding the vast, awe-inspiring universe that surrounds us. As we journey further into the exploration of Methuselah's mystery, we encounter yet another layer of complexity: the role that ancient stars like Methuselah play in shaping our understanding of the larger cosmic structure. While we have discussed its apparent age and its implications on stellar evolution and cosmology, the study of such ancient stars also sheds light on the early formation of galaxies and the intergalactic medium. These are areas of research that often remain in the shadows of more famous cosmic events like supernovae or black hole mergers, but they are just as crucial in piecing together the history of the universe. Methuselah and stars like it were likely formed in some of the earliest galaxies in the universe, galaxies that were born in the wake of the Big Bang. These first galaxies were vastly different from the ones we observe today. They were smaller, more turbulent, and much more prone to rapid star formation. The stellar populations within these galaxies, including the population 3 stars, were composed almost entirely of hydrogen and helium, the simplest elements in the periodic table. This marked a time when the universe had very little of the heavier elements that we now take for granted in our understanding of stellar chemistry. As these early galaxies evolved, so too did the stars within them. Stars like Methuselah, with their extreme age and lack of heavy elements, provide us with clues about the nature of star formation in the early universe. They are living fossils, so to speak, holding on to secrets about how the first stars lived and died, and how they enriched the intergalactic medium with heavier elements through processes like supernova explosions and the synthesis of elements in their cores. Studying Methuselah can give us insights into the very first stages of galaxy formation and how they evolved over time. But the story of Methuselah goes beyond its stellar composition and age. It also touches on the ongoing battle between theory and observation in astrophysics. For years, astronomers have tried to reconcile the age of stars like Methuselah with the age of the universe itself. The key issue here lies in the methods used to estimate the age of stars. One of the primary methods involves the use of stellar models that predict the rate at which a star will evolve based on its mass, composition, and other properties. For many years, these models have been quite successful in estimating the ages of stars in the Milky Way and other galaxies. However, the case of Methuselah has shown that there are limitations to these models, especially when it comes to stars that formed in the very early stages of the universe. The mystery of Methuselah's age also highlights the delicate balance that astronomers must strike when interpreting data. The methods used to measure the age of stars depend on a number of assumptions, many of which are based on our current understanding of stellar physics. However, the universe is far more complex than we can currently model, and as we discover more stars that challenge these assumptions, we are forced to rethink our models and refine our methods. This is a hallmark of scientific progress. New discoveries often lead to the revision of old ideas, and as we probe deeper into the mysteries of the universe, we are forced to confront the limitations of our current knowledge. There is another important aspect of Methuselah's story that is often overlooked: the impact it has on the search for life beyond Earth. Stars like Methuselah, though ancient, could have played a critical role in the creation of the elements necessary for life. In fact, many of the elements we associate with life, such as carbon, oxygen, and nitrogen, were created in the hearts of stars long before the Earth itself formed. As stars like Methuselah lived and died, they spread these elements throughout the cosmos, enriching the interstellar medium and making it possible for new generations of stars and planets to form. This process, known as nucleosynthesis, is one of the key factors that makes life possible in the universe. The heavy elements created in the cores of stars are essential for the formation of planets and the development of life as we know it. Therefore, stars like Methuselah are not just important for understanding the history of the universe. They are also crucial for understanding the origins of life itself. Without the heavy elements created by these ancient stars, life as we know it may not have been possible. In addition to their role in nucleosynthesis, ancient stars like Methuselah also have an impact on our understanding of the distribution of matter in the universe. The heavy elements that are produced in stars are not evenly distributed across the universe. Instead, they are spread out in a complex, often uneven manner, forming a cosmic web of gas, dust, and stars. This distribution of matter plays a crucial role in the formation of galaxies, the development of star systems, and even the way that light travels through the universe. By studying the composition of stars like Methuselah, astronomers can gain valuable insights into the large-scale structure of the universe and the forces that shape it. It's also worth noting that the study of ancient stars like Methuselah is not just about looking backward in time. It also has implications for the future of our own solar system. Our Sun, which is much younger than stars like Methuselah, is expected to eventually reach the end of its life and evolve into a red giant, shedding its outer layers and leaving behind a white dwarf. This process is something that all stars eventually go through, but the specifics of how this happens depend on the mass, composition, and other factors of the star in question. By studying stars like Methuselah, astronomers can gain insights into the future of our own star, helping us understand what might happen to the Earth and the other planets in our solar system billions of years from now. In many ways, stars like Methuselah represent the beginning and the end of the life cycle of stars. They are the oldest known stars in the universe, remnants of a time long past, yet they are also the building blocks for future generations of stars and planets. As we continue to explore these ancient stars, we are not just unraveling the mysteries of the past, we are also laying the groundwork for future discoveries about the nature of the universe, the origins of life, and the future of our solar system. And this is where the true significance of Methuselah lies. It is not just a star that challenges our understanding of the universe's age. It is a cosmic signpost, pointing the way toward deeper mysteries waiting to be uncovered. Its age, its composition, and its very existence are all invitations to look beyond the surface and dig deeper into the fundamental nature of the cosmos. Methuselah is not just an anomaly to be explained away. It is a reminder of how much more there is to learn about the universe, and how many mysteries still lie beyond our grasp. Through the study of Methuselah and other ancient stars, we are not only exploring the distant past, we are also looking toward the future. Every new discovery adds another layer to our understanding of the universe, revealing new patterns, new relationships, and new possibilities. The journey is long, and it is filled with uncertainty, but it is also filled with wonder and the promise of new knowledge. And in that sense, stars like Methuselah are not just ancient relics, they are the keys to unlocking the mysteries of the universe, helping us chart a course through the cosmos and understand our place in the grand, ever-unfolding story of existence. As we continue to delve into the significance of Methuselah, it is important to consider the broader implications that arise from studying such ancient stars. These stars provide us with an unprecedented opportunity to examine the origins of our universe, the formation of galaxies, and the processes that govern the evolution of stars. Methuselah and its counterparts offer a rare glimpse into the universe's distant past, a time when conditions were vastly different from the cosmos we see today. One of the most fascinating aspects of stars like Methuselah is their role in our understanding of the early universe, particularly in relation to the formation of galaxies. The first galaxies, which appeared shortly after the Big Bang, were composed primarily of hydrogen and helium. These galaxies were often small, irregular, and highly active in terms of star formation. As these galaxies evolved over time, they began to accumulate more complex elements, such as carbon, oxygen, and nitrogen. These elements, produced in the cores of stars, were then spread throughout the galaxy during events like supernovae or stellar winds. Methuselah's composition and its position in the universe offer insights into the conditions that prevailed during the early stages of galaxy formation. Its age and elemental makeup suggest that it formed during a period when the universe was still in its infancy, only a few billion years old. Studying stars like Methuselah allows us to piece together the puzzle of how the first galaxies were structured, how they interacted, and how they gave rise to the galaxies that we observe today. Furthermore, it allows us to better understand the processes that lead to the formation of the heavier elements that are crucial for the creation of planets and, potentially, life. In addition to their role in galaxy formation, stars like Methuselah also provide valuable information about the history of cosmic reionization. This process, which occurred about 1 billion years after the Big Bang, marks the point in time when the universe transitioned from being opaque to transparent. Prior to reionization, the universe was filled with a dense fog of neutral hydrogen gas that scattered light and made it impossible for photons to travel freely across vast distances. The process of reionization, driven by the intense radiation from the first generations of stars, cleared this fog and allowed light to travel freely across the universe. Methuselah, being one of the oldest stars, provides a unique window into this era of cosmic history. Its characteristics help astronomers refine their models of cosmic reionization and better understand the conditions that allowed the universe to transition from its early, dark state to the bright, transparent cosmos we see today. By studying stars like Methuselah, we are not only uncovering the past, we are also gaining insights into the forces that shaped the very structure of the universe as we know it. But the story of Methuselah is not just one of cosmic evolution and the formation of galaxies. It also has profound implications for the study of stellar physics. The age of Methuselah challenges many of our current models of stellar evolution, forcing astronomers to reconsider how stars form, live, and die. Stars like Methuselah, which are composed mostly of hydrogen and helium, have evolved in ways that are not fully understood. The discrepancy between the star's observed age and the age of the universe itself suggests that our models of stellar aging may be incomplete, or that there are unknown factors at play in the evolution of ancient stars. This discrepancy also raises questions about the accuracy of our methods for measuring the age of stars. Astronomers typically rely on a combination of techniques to estimate the age of a star, including the star's luminosity, temperature, and chemical composition. However, as we have seen with Methuselah, these methods are not always foolproof. The star's age is determined by comparing its properties to models of stellar evolution, but if these models are incorrect or incomplete, the resulting age estimate may not be accurate. In the case of Methuselah, the star's age estimate has been called into question multiple times, particularly because it appears to be older than the universe itself. Some astronomers have suggested that the star could be much younger than originally thought, or that it might be part of a population of stars with unique properties that we do not fully understand. Others have proposed that the discrepancy could be due to errors in the way the star's age is calculated. Regardless of the explanation, the mystery of Methuselah's age highlights the complexities of stellar astrophysics and the challenges of making accurate age estimates for stars that are as old as the universe itself. The case of Methuselah also underscores the limitations of our current understanding of the universe's early history. The age of the universe, as estimated by cosmologists, is based on a variety of observations, including the study of the cosmic microwave background radiation, the distribution of galaxies, and the expansion rate of the universe. However, the precise age of the universe is still a subject of ongoing debate, and new discoveries, such as the existence of stars like Methuselah, can sometimes challenge our assumptions about the universe's timeline. In many ways, Methuselah's age serves as a reminder of how much we still have to learn about the cosmos. While our current models of the universe have allowed us to make tremendous strides in understanding the fundamental laws of physics, we are still far from having a complete picture of the universe's origins and evolution. As we continue to study stars like Methuselah and probe the mysteries of the early universe, we will undoubtedly encounter new puzzles and paradoxes that will challenge our understanding of the cosmos. But it is precisely through these challenges that we will make the greatest discoveries, pushing the boundaries of our knowledge and expanding our understanding of the universe. The study of ancient stars like Methuselah also highlights the importance of ongoing collaboration between astronomers, physicists, and other scientists. The mysteries of the universe are not easily solved by a single discipline or approach. Instead, they require the combined efforts of scientists from diverse fields who can bring different perspectives and expertise to the table. In the case of Methuselah, astronomers have had to work closely with theorists, computational physicists, and even mathematicians to refine our models of stellar evolution and develop new techniques for measuring the age of stars. This interdisciplinary approach is essential for making progress in our understanding of the universe and solving the complex problems that arise from studying ancient stars. Furthermore, the study of stars like Methuselah has profound implications for the future of astrophysics and our quest to understand the fundamental nature of the universe. As we continue to develop more advanced telescopes and observational techniques, we will be able to study even older and more distant stars, pushing the limits of our knowledge even further. These new discoveries could lead to groundbreaking breakthroughs in our understanding of the universe's formation, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. The mysteries of stars like Methuselah are just the beginning. There is much more to discover, and the journey is far from over. The Methuselah Star is more than just the oldest known star. It is a key to unlocking some of the universe's greatest mysteries. Its age, composition, and position in the cosmos provide us with valuable insights into the early history of the universe, the formation of galaxies, and the evolution of stars. Methuselah challenges our understanding of stellar evolution, cosmic reionization, and even the age of the universe itself. As we continue to study this ancient star and others like it, we are bound to uncover new truths about the universe and its origins. Methuselah may be ancient, but its story is just beginning, one that will continue to captivate scientists and enthusiasts alike for generations to come. As we delve further into the nature of Methuselah, we must also consider how its existence challenges not only our understanding of stellar physics, but also the very fabric of our universe's timeline. The star's apparent age, older than the current estimates of the universe's age, forces us to question the assumptions we've made about the cosmos. Could there be hidden processes at work in the universe, unknown to us, that allow for the formation of stars like Methuselah, which seem to defy the logic of modern astrophysical models? Or could the tools and methods we use to measure such ancient celestial objects be flawed in ways we have yet to understand? Let's take a closer look at the broader implications of these questions and how they might shape the way we approach cosmology and astronomy in the future. One of the primary methods used to estimate the age of stars is the process of stellar evolution, which tracks how a star changes over its lifetime. Stellar models predict that stars like Methuselah, which are classified as population 2 stars, should have formed in the early universe, around 13 billion years ago. These stars are generally composed of fewer metals than younger stars, as they formed before the first generations of supernovae could spread heavier elements throughout the cosmos. The discrepancy between the star's observed age and the age of the universe challenges these models and suggests that there might be a gap in our understanding of the physics that governs such ancient stars. For decades, scientists have relied on the standard model of cosmology, known as the lambda cold dark matter (lambda CDM) model, to estimate the age of the universe. This model incorporates a variety of data sources, such as observations of the cosmic microwave background radiation, galaxy redshift surveys, and supernova measurements, to determine the expansion rate of the universe and the time that has passed since the Big Bang. Based on these observations, the universe is thought to be approximately 13.8 billion years old. However, stars like Methuselah appear to challenge this estimate, as their age, measured by traditional stellar dating methods, seems to exceed this number. This discrepancy has led some scientists to reconsider the precision of our age estimates for both the universe and its oldest stars. The issue isn't just about the age of one particular star. It has broader implications for how we calibrate our cosmic timeline. Could it be that the age of the universe is slightly older than we currently believe? Or is there an entirely different explanation for the apparent age of stars like Methuselah? The mystery surrounding the age of Methuselah also brings to light the limitations of current methods of measuring stellar ages. Age estimation is an inexact science, particularly for stars that are as old as Methuselah. Astronomers typically use a combination of techniques, including isochrone models, asteroseismology, and stellar evolution simulations, to determine a star's age. However, these methods rely on a number of assumptions and approximations that may not hold true for very ancient stars. Isochrones, for example, are theoretical curves that represent the positions of stars at different ages in a diagram plotting luminosity against temperature. By comparing the position of a star on this diagram to the theoretical models, astronomers can estimate its age. However, this method is only accurate for stars that are relatively young or at least in their main sequence phase. For older stars, particularly those that have exhausted their hydrogen fuel and are in the later stages of their lives, these methods become much less reliable. Astroseismology, which involves studying the vibrations of stars, has also been used to estimate the age of stars by measuring their internal structure and oscillations. This technique provides valuable information about the star's density, size, and temperature, which can be used to refine age estimates. However, like isochrone models, astroseismology also relies on assumptions that may not always apply to the oldest stars, especially when these stars show unique features that differ from those of younger stars. In the case of Methuselah, these traditional methods have produced results that suggest the star is older than the universe itself. While this has prompted some scientists to reevaluate their models of stellar evolution, it has also spurred a rethinking of the very methods used to measure stellar ages. Could it be that there are unknown factors that influence the evolution of ancient stars? Or perhaps, as some scientists have suggested, the discrepancy could be the result of an error in the way the star's age has been calculated. To complicate matters further, stars like Methuselah do not follow the expected patterns of stellar evolution that are observed in younger stars. The star's luminosity, temperature, and chemical composition all suggest that it has been in its current state for much longer than the models would predict. This raises an intriguing question. Could Methuselah be an anomaly in the stellar population, or is it part of a larger class of stars that we have yet to fully understand? In the search for answers, astronomers have begun to explore new ways of modeling stellar evolution. One approach is to develop more sophisticated simulations that take into account the complex interactions between stars and their environments. These simulations might allow for a more accurate understanding of how stars like Methuselah evolve, potentially revealing new factors that influence their lifetimes. By refining our models of stellar evolution and incorporating the latest observational data, we can begin to build a more comprehensive picture of how ancient stars like Methuselah came to be and what they can tell us about the early universe. Beyond the technical aspects of measuring the age of stars, the mystery of Methuselah has profound philosophical implications. It forces us to confront the limitations of human knowledge and our ability to understand the vastness of the universe. We live in a universe that is so old, so complex, and so far-reaching that even our most sophisticated tools and theories can barely scratch the surface of its mysteries. Stars like Methuselah are a reminder of how much we have yet to discover and how much more there is to learn about the universe we inhabit. As we continue to study the cosmos, we must embrace the idea that there will always be more questions than answers. The universe is a vast, ever-changing expanse, and every discovery we make only leads to more mysteries. The study of stars like Methuselah encourages us to think beyond the limitations of our current understanding and to approach the cosmos with an open mind, ready to challenge our assumptions and push the boundaries of knowledge. The mystery of Methuselah also raises the question of how stars like it will continue to influence our understanding of the universe in the future. As new telescopes and observational techniques are developed, we will gain even more insight into the nature of these ancient stars. Future missions, such as the James Webb Space Telescope, are poised to provide unprecedented views of the cosmos, allowing us to study stars like Methuselah in greater detail than ever before. These new observations could help to resolve the mystery surrounding the star's age and provide clues about the processes that govern the evolution of the oldest stars in the universe. Methuselah is more than just an ancient star, it is a symbol of the mysteries that still lie hidden within the universe. Its age, which appears to exceed the current estimates of the universe's age, challenges our understanding of stellar evolution, the timeline of the cosmos, and the methods we use to measure the passage of time in the universe. The study of Methuselah and stars like it forces us to question our assumptions, rethink our models, and embrace the unknown. As we continue to explore the mysteries of the cosmos, we are reminded that the universe is full of surprises, and every discovery opens up new avenues for investigation. Methuselah may be one of the oldest stars we know, but it is far from the last mystery the universe has to offer. As we consider the implications of Methuselah's age on our broader understanding of the universe, it's crucial to reflect on the ways in which such discoveries reshape not only the science of astronomy but our very perception of time itself. The existence of such an ancient star, one that seems to contradict well-established models, forces us to reconsider fundamental assumptions about the universe's origin, structure, and ultimate fate. The discovery of Methuselah and the resulting puzzle over its age highlights a critical aspect of science, the ever-evolving nature of our understanding. It serves as a reminder that scientific knowledge is not fixed. Rather, it is a fluid, dynamic process driven by new data, refined methodologies, and occasionally, the humbling realization that much of what we believe to be true may need to be revised or even discarded in the face of new evidence. What makes the Methuselah Star particularly intriguing is not just its age, but the broader implications for cosmology. When we examine the larger picture, we must ask, what does it mean to measure time on a cosmic scale? How do we measure the lifespan of an object that, in many ways, defies our understanding of the cosmic clock? The concept of cosmic time itself is a fascinating area of exploration. In human terms, our entire civilization is but a blip in the grand timeline of the universe. But when we think about stars, particularly those as ancient as Methuselah, we are forced to confront the vast, nearly incomprehensible scales of time that govern the life cycles of celestial objects. Stars, even the oldest among them, live out lifetimes that span millions or billions of years. In the case of Methuselah, its age seems to eclipse even the age of the universe itself, forcing us to reconsider not only how we measure time but what we consider to be the limits of that time. One of the ways astronomers currently measure the age of stars is by studying the process of stellar nucleosynthesis, which occurs when a star fuses lighter elements like hydrogen into heavier elements like helium and eventually, depending on its mass, into even heavier elements such as carbon and oxygen. These processes release enormous amounts of energy, and are what allows stars like Methuselah to shine. By examining the elements in a star's spectrum, scientists can gain insights into its chemical composition, and by extension, its age. However, this process is not foolproof. For stars that are as old as Methuselah, their chemical composition may have been altered over billions of years due to processes such as stellar mergers or accretion of gas from nearby cosmic structures. These alterations make it more challenging to pinpoint a star's exact age. Methuselah is part of a group of stars known as Population 2 stars. These stars are among the oldest in the universe, formed during the early stages of the cosmos when heavy elements were scarce, and the universe was largely made up of hydrogen and helium. Population 2 stars typically contain very few metals, which are elements heavier than hydrogen and helium. In contrast, younger stars, particularly those of Population 1, contain a higher proportion of metals, a result of supernovae explosions from earlier generations of stars that enriched the surrounding interstellar medium. The age of Population 2 stars can therefore provide us with valuable information about the early history of the universe, and their study helps astronomers piece together the timeline of stellar evolution. Despite their ancient origins, these stars still possess remarkable longevity. Methuselah, for example, is a massive, blue giant, meaning it has consumed a large portion of its nuclear fuel but has yet to exhaust its resources. Stars like this are still in the later stages of their life cycle, slowly transforming into red giants before eventually shedding their outer layers to become white dwarfs, or, for the most massive among them, collapsing into black holes. The fact that Methuselah has existed for as long as it has, despite its age, suggests that its evolutionary path is particularly unique, further complicating our understanding of stellar life cycles. Understanding the Methuselah star also requires a look at the broader context of stellar evolution. As stars age, they undergo various stages of transformation. The most significant transformation occurs when a star exhausts the hydrogen in its core. This marks the transition from the main sequence stage, when a star is stable and in equilibrium between gravitational collapse and nuclear fusion, to the red giant phase. During this phase, the star's outer layers expand, and its core contracts. The fate of the star depends on its mass. Low-mass stars, like our Sun, will eventually shed their outer layers and become white dwarfs, while more massive stars may explode in a supernova and leave behind either a neutron star or a black hole. For stars as old as Methuselah, the rate of nuclear fusion has slowed considerably, and their outer layers are likely to have expanded significantly. This means that, while Methuselah may appear brighter than younger stars, it is not as energetic as it once was. In fact, the star's apparent brightness could be one of the factors that have allowed astronomers to study it in detail. By carefully observing its light and analyzing its spectrum, scientists can glean clues about its size, temperature, and chemical composition. The fact that Methuselah appears to be more than 14 billion years old raises additional questions about the processes that govern stellar birth and death. How, for example, did stars like Methuselah form in the first place? Most stars are thought to form in dense molecular clouds, where gas and dust particles collapse under their own gravity to create a protostar. These clouds, however, are often rich in metals, which complicates the formation of population II stars. According to current theories, population II stars like Methuselah must have formed from a primordial gas cloud, one that lacked the heavier elements created by earlier generations of stars. This suggests that the first generation of stars in the universe, known as population III stars, must have been composed almost entirely of hydrogen and helium. These stars would have been far larger and hotter than those that came after them, and their explosive deaths would have seeded the universe with the heavy elements needed for the formation of later generations of stars, planets, and even life itself. The implications of Methuselah's existence extend far beyond the realm of stellar physics. They touch on the very nature of time and the way we perceive the universe. The universe is a vast and intricate web of objects and phenomena, all interconnected in ways we are still learning to understand. Every discovery in astronomy, whether it's a new star, galaxy, or cosmic event, adds another layer to our comprehension of the universe's origins, its present state, and its ultimate fate. Stars like Methuselah serve as windows into the past, offering us a glimpse of the universe as it once was. And in doing so, they challenge us to rethink everything we thought we knew about the cosmos. Ultimately, the mystery of Methuselah is not just about a single star, but about the very nature of our existence within a vast, unfathomable universe. It is a symbol of the many mysteries that still remain, reminding us that there is much we have yet to understand. With each new discovery, we are forced to confront the limits of our knowledge, and it is through these moments of discovery that science progresses. The Methuselah Star may be old, but its secrets are just beginning to unfold, and the quest to understand it may lead to breakthroughs in our understanding of the universe that we cannot yet predict. The future of astronomical research holds the promise of more discoveries like Methuselah. As technology continues to advance, and new telescopes and instruments are developed, we will be able to peer deeper into the cosmos and uncover more stars, galaxies, and phenomena that challenge our understanding of the universe. The journey to uncover the true nature of stars like Methuselah is just beginning, and who knows what incredible revelations await us as we continue to push the boundaries of human knowledge. The pursuit of knowledge about Methuselah is far from over. While the discovery of such an ancient star has sparked a wealth of intriguing questions, it has also propelled new research and exploration in the field of astrophysics, cosmology, and stellar evolution. As we continue to peer into the depths of the universe, the Methuselah Star remains a focal point, challenging astronomers to refine their methods, rethink their models, and consider alternative explanations for the discrepancies we encounter. For example, one area that holds particular promise for further investigation is the role of dark matter and dark energy in the formation and evolution of stars like Methuselah. Both dark matter and dark energy represent two of the greatest mysteries in modern physics. They are thought to account for the majority of the universe's mass and energy content, yet we cannot directly observe them. Dark matter, in particular, is believed to be responsible for the way galaxies rotate and hold themselves together, while dark energy is thought to drive the accelerated expansion of the universe. Could these enigmatic forces have played a role in the formation of the ancient stars we observe today? The question of whether dark matter or dark energy could have affected the formation of stars like Methuselah is still an open one. However, there is increasing evidence to suggest that the early universe may have been very different from what we observe today. It's possible that the interplay between dark matter and dark energy could have influenced the processes that led to the formation of population II stars. For example, dark matter may have provided additional gravitational pull, helping to compress gas clouds and kickstart the process of star formation. Alternatively, dark energy's effects on the expansion of the universe might have shaped the rate at which stars formed in the early cosmos. Another exciting frontier for research involves studying the chemical composition of ancient stars like Methuselah. Stars are essentially cosmic laboratories, where the elements that make up the universe are forged through the process of nuclear fusion. By studying the chemical signatures of stars like Methuselah, astronomers can gain valuable insights into the conditions of the early universe, as well as the origins of the elements that make up everything from planets to life itself. This process is known as stellar nucleosynthesis, and it is one of the primary ways in which scientists study the birth of elements like carbon, oxygen, and iron. Methuselah's unique composition suggests that it may have been part of the very first generation of stars, formed from a pristine mixture of hydrogen and helium that existed in the early universe. The heavy elements that are now abundant in the universe, elements that are essential for life, would not have been present in these first stars. Instead, they were created later, during the explosive deaths of these early stars, through supernovae and other violent processes. Understanding the chemical composition of stars like Methuselah is key to understanding how the universe evolved and how the building blocks of life came to be. Moreover, the Methuselah Star provides an invaluable opportunity to study the dynamics of star clusters. Many of the oldest stars in the universe are found in globular clusters, dense collections of stars that are often much older than individual stars found in isolation. These clusters can provide astronomers with a natural laboratory for studying the interactions between stars in a dense environment. In the case of Methuselah, it is part of a globular cluster, and its study could help scientists understand how stars in these clusters evolve, interact, and survive over billions of years. The discovery of Methuselah could therefore provide clues about the mechanisms that govern stellar evolution in these ancient environments. As scientists continue to study Methuselah, it will also be important to improve the precision of age determination techniques. Currently, one of the biggest challenges in stellar astronomy is accurately measuring the age of stars. This is because there are many factors that can influence a star's appearance, including its chemical composition, rotation, and magnetic activity. In the case of Methuselah, the age estimates have varied depending on the methods used and the assumptions made. For instance, one of the most common techniques involves modeling a star's luminosity, temperature, and chemical composition to estimate its age. However, this method is sensitive to the accuracy of the underlying models and the assumptions made about the star's evolutionary history. Recent advancements in technology and observational techniques may allow for more precise measurements of stars like Methuselah. New telescopes, such as the James Webb Space Telescope, will enable astronomers to observe stars in unprecedented detail, improving our understanding of their age, chemical composition, and evolution. Furthermore, advances in computational methods and simulations of stellar evolution will allow for more accurate predictions of how stars evolve over time. These breakthroughs could help resolve the age discrepancy surrounding Methuselah and provide deeper insights into the lives of the oldest stars in the universe. Ultimately, the study of Methuselah is part of a broader effort to understand the history of the universe itself. The universe, with its vast expanses and billions of galaxies, is a complex and ever-changing entity. Yet, stars like Methuselah offer us a glimpse into the very beginning of that cosmic history. They are living fossils, remnants of the earliest epochs of the universe, and their study allows us to look back in time, to a point before galaxies, planets, and even life itself existed. By studying these ancient stars, we can uncover the secrets of the early universe and gain a better understanding of the processes that shaped the cosmos as we know it today. The discovery of stars like Methuselah invites us to challenge our assumptions about the universe's origins and its future. While it is easy to assume that our current understanding of the cosmos is complete, the reality is that we are just beginning to scratch the surface of the mysteries that lie beyond our sight. Methuselah, in all its ancient glory, serves as a reminder that the universe is far older, more complex, and more mysterious than we could have ever imagined. It is a symbol of the wonders that await us as we continue our journey of exploration, and a testament to the power of curiosity and scientific inquiry. As our understanding of the cosmos grows, and as we continue to unravel the mysteries of stars like Methuselah, we may one day come to understand not just how this star came to be, but how it fits into the larger narrative of the universe itself. The answers may not come easily, and they may take decades, centuries, or even millennia to uncover. But the pursuit of knowledge, the quest to understand the fundamental truths of the universe, is one that will continue to drive humanity forward. And as we gaze up at the stars, like Methuselah, we will be reminded of the vast, untold stories that lie waiting for us to discover. Methuselah, named after the biblical patriarch said to have lived the longest, remains one of the most compelling enigmas in astrophysics. This solitary star, officially designated HD 140283, is more than just a glowing sphere of hydrogen and helium. It is a cosmic paradox that threatens to destabilize our most cherished timelines of the universe. Why? Because its age, as estimated by rigorous scientific methods, challenges the very age of the universe itself. At one point, estimates placed Methuselah's age at about 14.46 billion years. And yet, the age of the universe, as derived from the most accepted cosmological models and data from the cosmic microwave background radiation, sits at roughly 13.8 billion years. The implications are immense. To understand just how bold this contradiction is, one must first appreciate the precision with which cosmologists have calculated the universe's age. The cosmic microwave background (CMB), the afterglow of the Big Bang, has been studied in exquisite detail by satellites such as WMAP, Wilkinson Microwave Anisotropy Probe, and later, the Planck Space Observatory. These observatories have mapped tiny temperature fluctuations in the CMB, providing insight into the early density variations in the universe, which eventually gave rise to galaxies and clusters. From this, cosmologists deduce a timeline, an unfolding story of the universe stretching back 13.8 billion years. So, when a single star appears older than this cosmic benchmark, it demands attention. It either signals a flaw in our stellar age-dating methods, an error in our cosmological model, or perhaps even points to new physics waiting to be discovered. The star itself is relatively nearby in astronomical terms, just about 190 light-years from Earth, situated in the constellation Libra. It's a population 2 star, meaning it's part of an early generation of stars formed not long after the Big Bang. These stars are characterized by their extremely low metal content, metals, here referring to any elements heavier than helium. In Methuselah's case, the metal content is so low that it reinforces its classification as ancient. It lacks the heavy elements formed in later generations of stellar evolution. Instead, it appears to have formed from material that had been very lightly polluted by the first supernovae that exploded in the young universe. Methuselah's trajectory through space is also unusual. It's on a highly elliptical orbit that carries it far above and below the galactic plane, a trait shared with many halo stars. This suggests it might not have formed in our galaxy at all. Some researchers speculate that Methuselah could have originated in a smaller satellite galaxy that was later absorbed by the Milky Way. If true, this would add an additional layer of complexity to its already fascinating narrative, a tale not just of extreme age, but of intergalactic travel and cosmic migration. What makes the Methuselah star's estimated age so compelling is the methodology behind its measurement. Astronomers use a technique known as stellar modeling, which involves comparing a star's observed properties, like its temperature, luminosity, and metallicity, to theoretical models of stellar evolution. These models describe how stars of various masses and compositions change over time. Methuselah's low metallicity and subgiant status, its transitioning from the main sequence to the red giant phase, make it an excellent candidate for precise age estimation, since these characteristics evolve in well-understood ways. However, the margin for error is always present, and various revisions over the years have adjusted the star's age estimate downward, from 14.46 billion years to closer to 13.7 or 13.5 billion years, depending on the assumed chemical abundances and the model parameters used. Even the smallest tweaks to these assumptions can lead to significant changes in age estimates. For instance, if we assume a slightly higher oxygen-to-iron ratio, or if we adjust the opacities, how transparent the stellar material is to radiation, the star's age estimate could drop within the bounds of the universe's age. This is where astrophysics begins to flirt with philosophy. Are we seeing the limits of our modeling tools? Or are we brushing up against deeper truths that our current theories cannot yet explain? Consider also the broader implications of such an old star existing within our galactic neighborhood. If Methuselah formed just a few 100 million years after the Big Bang, it would place it among the second generation of stars ever created. The first generation, known as population 3 stars, is theorized to have been composed almost entirely of hydrogen and helium. These stars would have been massive, luminous, and short-lived, burning through their fuel in just a few million years before exploding in supernovae. These violent deaths would have seeded the cosmos with heavier elements, carbon, oxygen, iron, the very materials needed for life as we know it. Methuselah, as a population 2 star, may have been born from one of the first clouds of gas enriched by these early supernovae. Its composition, then, is a snapshot of the universe in its infancy, a relic of a time when galaxies were still forming and the cosmos was a far darker and simpler place. In fact, Methuselah's story could help inform our search for population 3 stars, a holy grail in modern astronomy. Despite decades of searching, not a single population 3 star has been observed directly. They may have all long since burned out and exploded. But by studying stars like Methuselah, we can make inferences about the types of environments these primordial stars must have existed in. Every low metallicity star gives us a clue, a puzzle piece in the grand mosaic of cosmic history. The implications stretch beyond just stellar evolution and into the realm of cosmology itself. If it were ever conclusively proven that Methuselah or any other object is older than the universe, it would force a re-evaluation of everything from the Big Bang model to the rate of cosmic expansion. This, in turn, would impact our understanding of dark energy, the mysterious force driving the universe's acceleration. It could even hint at more exotic possibilities, such as a cyclic universe, one that undergoes repeated births and deaths, or a multiverse, in which our observable universe is just one bubble among many. Each of these theories, while still speculative, gains plausibility in the face of anomalies like Methuselah. At the same time, it's important to temper excitement with scientific rigor. The majority of researchers still believe that the age discrepancy can be resolved through better measurements and improved models. The error bars in both the age of the universe and the age of Methuselah overlap when accounting for uncertainties. But that doesn't diminish the importance of such outliers. In science, anomalies are not to be swept under the rug, they are to be studied, scrutinized, and understood. Methuselah is a flag planted in the fog of our ignorance, a signpost that there is still much we do not know. And perhaps that is Methuselah's greatest gift, its ability to inspire wonder. In a world where so much of science has become specialized and abstract, here is a single star, glowing in the sky, that defies our expectations. It bridges the gap between science and mystery, between data and philosophy. It invites us to look up, to question, to explore. In that way, Methuselah does more than illuminate the heavens, it lights the path forward, urging us onward into the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.